before we do get started today, let's just go over a little bit about what's coming up. I think you probably are aware of this, but in case some of you aren't, I want to make sure. The good news, bad news situation, right? Good news is next week is Thanksgiving week, so Thursday and Friday is a state holiday. Okay. Now, the bad news is we have professional meetings Monday, Tuesday, and Wednesday. That means there's no classes next week. Sorry about that. Just get over it. Okay. So, you'll be, if you have any business to do with the school, though, the college is open Monday, Tuesday, and somewhat on Wednesday. Talk about that in a minute. So anytime during normal working hours, basically 8 to 5-ish or so, you should be able to take care of any business you have with the college Monday and Tuesday. Now, if you're trying to see an instructor Monday or Tuesday, a lot of the instructors and other people will be down in Mobile at those professional meetings. A lot of us are not going to Mobile. We'll have professional meetings, but not here on this campus, over on the Birmingham West campus. Okay? Yeah, we no party. Okay, unfortunately, but that means if you're trying to get in touch with an instructor, we're going to be in meetings and not going to be at our office, not going to be here at the telephone. So, out of luck there. However, Wednesday, they're supposed to give us office time, so we should be back in our offices on Wednesday. So if you do need to see us, try to contact us, and I would say Wednesday morning-ish, okay? The reason I say that, and this is the same thing about if you have business with the college, if you are going to put it off until Wednesday, get it done Wednesday morning, because they often, not always, and it's not required or guaranteed or anything, but they often let us go a little early on the day before a major holiday like Thanksgiving. So, I would say if you have business with the college, all day Monday, all day Tuesday should be fine. I'd say get it done Wednesday morning. Now, the offices may still be open Wednesday afternoon in the early afternoon, but I don't know when they might be closing, so be sure you get it done in the morning on Wednesday. That's the same thing about seeing an instructor. We'll be in meetings Monday and Tuesday, so if you do need to see one of us, come and see us Wednesday morning-ish. Yeah. Well, it will be welcome, because I got to drive to Georgia as soon as they let me go. I'm on the road. I'll be packed and everything. My wife will already be over there. Yes.
Are you sure that we're out next week?
I'm sure that there are no classes next week, right? Yeah. Have some of your other classes told you they're meeting?
Yesterday my professor told me there's not going to be no classes next week.
Yeah, there aren't any classes next week at all. Okay? No. Okay. And certainly no Saturday classes either, in case you thought, what about Saturdays? They're off too. All right. Now, that's pretty much us here. Now, what are we doing in this class? Okay? We got to finish chapter 4 today, and hopefully get started on 6. We don't do chapter 5, and if you have the small thin books, you'll notice 5 isn't even in there. Okay? So we go right into 6, which is electricity and magnetism. Now, I fear that we might not get far enough along for the first lab today, but we're going to do it anyway. And here's why. The week after we get back from Thanksgiving, sorry about this, folks, but on that Thursday, my wife has already ordered tickets, and we've got them for something somewhere in downtown Birmingham. It's kind of her early birthday present, and so I'm going. Okay, so I'll be here for class, but lab time pretty much is going to be wiped out, because I've got to head downtown to head home to go to the presentation. I don't know if any of you know Martin Short and Steve Martin, but they got a 2-man show going on somewhere, Alabama Theater Huh?
Does your wife teach also?
She's at UAB. She's a researcher. Yeah.
I thought you said she wrote books.
Huh?
Did you say she wrote some books?
Not books. She's written many papers,
Research.
research papers, and she's been author or co-author on several chapters in books, you know, and things like that. But yeah, that kind of stuff. So in other words, that Thursday we will have class, but there'll probably be no lab that day. So we need to get all the labs done that we can. We've got the first lab, second lab, and that would be when the third lab for that chapter is done. So we'll be, that will be the following week. So we just have enough days to manage to squeeze that in. All right. Any questions? And by the way, since we will finish chapter 4 today, unfortunately, first day back, Tuesday after Thanksgiving, we'll have the test on chapter 4. Okay. So I'll give you time to catch up. And you need test 1 and 3 on Birmingham tomorrow. Got them in my thing. Just wanted to make sure they're right. Okay. So let's pick up where we left off last time. We had talked about the phase changes, and this slide is not in your book, but I thought it was worth at least hitting. Because we did do this in the lab, so let's talk about it. When you're changing from a solid to a liquid, that is called the latent heat of fusion. This is a phase change. Remember, there's no temperature changes when you're changing phases, okay? A few of you put faces on your lab. I guess I wasn't pronouncing very clearly, but these are phase changes, not phase changes. That's a completely different issue. Okay, so that's called the latent heat of fusion, okay? Now, it's the same thing coming back the other way, from a liquid to a solid. When you're removing heat, it's also called the latent heat of fusion, okay? Now, you can call it the latent heat of melting if you're going from solid to liquid, or freezing when you're going from liquid to solid, but the catch-all name is fusion. When you're going from a liquid to a gas, that's called the latent heat of vaporization. Now, one we did not mention, but this mentions it, is you can, in certain circumstances, go directly from a solid to a gas. And that's called the latent heat of sublimation. Now, you've probably all seen this happen before, whether you realize that's what was happening or not. Have any of you ever had any occasion to mess with dry ice? Okay, dry? Huh?
Oh, yeah, we used to get it off the milk
Yeah.
trucks and put it in cocoa bottles and watch it blow up.
Yeah, okay. You know what dry ice is? Solid carbon dioxide. It's been chilled to a very low temperature, and then when it's and that's why it can keep things cool. I was on 1 year in between employment at Southern Research Institute, where I worked for about 8 years before our entire group was let go because we lost funding. Congress changed, and the EPA was no longer allowed to fund external projects. They had to do it all within. So we were let go. And so about a year I was just doing whatever jobs I could. And one of those jobs that I got was a soil sampling for a lawsuit. This was over in Anniston at the old Monsanto plant. Somebody else owned it by then. And they had been dumping PCBs into creeks and waterways. And later they found out those were carcinogenic, and people were getting cancers that lived along there. So it was a big lawsuit. Never knew which side of the lawsuit I was sampling for, but both sides were there, and neither one of us seemed to know who we were doing for. But we were taking the samples, and they were overseeing that. And we had to send the samples to the labs, and we sent them with dry ice so they wouldn't change the chemical composition during the shipment. Okay?
Dry ice keeps cold.
Oh, very long time, yeah.
If you really want to go by Publix and buy some dry ice and put that in your food,
Yeah.
it'll
Now,
last a while.
but let me warn you this, if you're using those little cheap styrofoam coolers, the dry ice, it gets it so cold it becomes brittle and they just fall apart. So you have to have a pretty good cooler if you're going to be putting dry ice in it. So yeah, it's there. That's sublimation. At normal temperature, at normal temperatures and pressures, carbon dioxide goes directly from a solid to a gas. You'll never see dry ice and have a puddle of liquid carbon dioxide. It just doesn't happen. It goes straight to gas. Now, I bet you more of you than have acknowledged it have actually seen dry ice before. Have you ever been to a concert when they had that misty, smoky-looking stuff going on during the concert? That was dry ice. Okay, well, dry ice was causing that. What was happening with all those bodies in the room, there was a lot of moisture in the air, and the dry ice, when it was, sublimating, becoming carbon dioxide gas, dropping the temperature greatly, and when it dropped the temperature, water droplets in the air started fogging up. And that's exactly what it was. It was fog from water. Okay, now, the temperature at which latent heat of fusion happens, that is the melting point. That's if you're going from solid to liquid. Of course, if you're going from liquid to solid, it's the freezing point, which is exactly the same temperature, okay? For water, that would be 0 degrees Celsius, 32 degrees Fahrenheit. When you're going from a liquid to a gas, you call it the boiling point. Of course, if you're going from a gas to a liquid, it would be the condensation. Oh, I'm sorry. That's next row shows that. Okay, shouldn't be saying that. Okay, and then if you're going from the solid to gas, that's called the sublimation point. They use the same term there for everything. Justin's here. If I can find it. There you go. Okay. Does anyone else come in since I called roll? Okay. Now, then if you're going in the other way, still sublimation point, even if it's going from a gas to a solid. It's weird to think of that, but it does. Condensation point if it's going from a gas to a liquid. Freezing point if it's going from a liquid to a solid. So those are the titles of that. And these are the same temperatures, these are the same temperatures, those are the same temperatures, at the same pressures. Pressure is really highly involved with that. Different gases. Some materials, you have to get it to really strange temperatures before you'll have that happen, or really strange pressures.
That's not in the book.
No, the sublimation part is not in the book. Or if it is, it's not.
The size change.
Yeah.
That's okay. I took a picture.
Yeah. And I don't see it in this. In an earlier text, it was. They left it out of this one, earlier edition. Okay, now we're ready for evaporation and condensation. This is on page 105. This is in the book. Okay? Now, what is happening when that is occurring? Do you have to wait till the vaporization point before you get any evaporation? If you've really paid attention to things in general life, you'll know that's not true. If you have a pan of water sitting out here on the table at room temperature and leave it out there long enough, it's going to evaporate. And you know it didn't come anywhere close to the boiling point. Okay? Why is that? Because you're looking at a macroscopic phenomenon, but it's happening on a microscopic scale. The individual molecules can change phase at any time. It just depends on if they've got enough energy to do so. Okay? Because some molecules may be moving very slowly and some very rapidly. Remember that the graph we did from Zizou's experiment that showed the distribution at different speeds, how many molecules are at certain temperatures, and the hump moves back and forth when you raise or lower temperature. They cover a wide range of energies, okay? So you can have some molecules that are very energetic and they could escape. Others that are not so energetic, they'll stay in the pan, okay? So evaporation is you have the energy required to overcome the phase cohesion. Let's talk about water. Those water molecules tend to hang together really tightly because of hydrogen bonding. But if one gets energetic enough, gets hit by other molecules or something, it may get enough energy and it'll leave and become a vapor. The higher energy molecules near the surface will then escape. Okay? And guess what? the higher energy molecules will be near the surface, because the more their energy they have, the more they bounce around, the further apart they get, so they are less dense and they rise. The slower, colder molecules sink to the bottom, and the higher energy molecules can then escape.
I'm thinking of a pot of boiling water.
Okay.
When it starts to boil, it's
Yeah.
no bubbles, but then the bubbles start right on the bottom of the pan.
Yeah. Now, what those bubbles are air bubbles that are getting released. The boiling of the water.
In other words, you're saying the H2O, the O's separate.
Yeah, the water molecules start separating from each other when the whole pot is boiling, and you see steam coming out. The initial bubbles, those are air molecules. See, water has a certain amount of air dissolved in it, okay?
H2O?
No, air dissolved in it. Not hydrogen and oxygen, air. Nitrogen, oxygen, carbon dioxide, everything that's in air was dissolved in water too. Now, how do you know that? Because fish living under the water breathe in their gills, take out the dissolved oxygen from the air dissolved in water.
Okay.
Yeah, they have to have that, okay? Otherwise, they wouldn't live. So, yeah. So those first bubbles you see are air bubbles that, as the water heats up, those are escaping. And then when it reaches a boil, then they're all coming out. You know, the water molecules are separated. So that's what you see.
On top, yeah.
Yeah, it's bubbling everywhere, yeah. But you'll see that basically when you watch it, you'll see the middle is doing this, and it kind of goes that convection stuff, you know, because the sides of the pan are usually a little cooler, the middle of the pan is usually a little hotter, okay? So the higher energy molecules escape near the surface. Now, condensation, that happens the other way. If you have a glass of cold water, now it wouldn't happen so much in the room now, okay? But in the summertime, especially if you didn't have good air conditioning, okay? You put a glass of cold water down on the table immediately. Water molecules in the air start condensing on the cold glass, okay? We were doing radon research when I worked for Southern Research Institute, and we had a big meeting down in Florida. And one of the honchos that had started off and done a lot was a guy named Terry Brennan from upstate New York, and he was really sharp guy, and but he had never been down south very much, okay? And the meetings were in Orlando, and he went there, and summertime, very humid, and what's more, the meeting room was near the indoor pool, so we had a lot of moisture in the air from there, and he could not believe it. A dry glass, you pour ice water, and immediately, he had never seen condensation show up that quickly, because up in upstate New York, just never was that humid, okay? Or if it was, it was at cooler temperatures, okay? Never had seen that happen. He was just amazed by it, that it can happen so quickly. The gas molecules near the surface lose kinetic energy, and then they come back to being a liquid again. All right, here is what is, the first part is illustrated. Here's a bunch of molecules, and there's way more molecules than this in here, but just let these circles represent bunches of molecules that are same number of bunches in every one, or either 5 kinetic energy. You could think of joules or whatever, but it doesn't matter. Kinetic energy of 5, joules wouldn't work, I don't think. A bunch more at 10s, and a bunch more at 15s, and some at 25s. Well, generally the 5s are going to settle toward the bottom, the 10s in the middle, the 15s, and the 25s are going to be more at the top. Because they're higher energy, they get further apart, they're less dense. Well, these 25s, if they do escape and go to air, because if that's enough energy for them to escape, then what you have before they escape, if you add up all these energies, 25, 50, 60, 70, 80, 95, 100, 110, 5, and 110. well, 115. I mean, yeah, 115. Divide that by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you have on average 11.5 kinetic energy. These are relative units, 11.5 kinetic energy. What if we lose those 225s? Now you're down to subtract 50 from 115, and you've got 65. Divide that by 8. I won't do the math. I'll let you see what it is. 65 divided by 8, your average kinetic energy is down to 8.1. Okay? Now, I don't know if you've ever realized this, but have any of you gone, say, hiking and stuff like this and carried a canvas bag of water, sort of it's not really a bag so much, but it's a canvas bag. Well, what happens is the canvas is always slightly losing, it sort of wicks out the water and it evaporates. So when you drink that water, it feels and senses to be much cooler than the surrounding atmosphere because of that evaporation concept here. Your kinetic energy, average kinetic energy, is dropped because of that evaporation of water. Now, this happens more so out west where it's pretty dry air, especially if you're, say, mountain climbing and that kind of stuff. Not that I've ever done any mountain climbing, but here's Tyler. But out doing hiking in the mountains out west where it's pretty dry, those canvas bags, the water tastes nice and cool, even though there's no ice in it. And that's because of this. Here in the southeast where it's so humid, not enough of it evaporates, it don't taste like tepid water, which is exactly what it is. But out there they do actually do that, and the water will be cooler than it would otherwise because the average kinetic energy is lessened when it evaporates. They're representing kinetic energies. They're not any particular unit. They're just representing high kinetic energy, lower kinetic energy. And when you lose the two highs, that drops your average kinetic energy from 11.5 to 8.1. So your temperature drops.
So you get, one bit, you just add those numbers together.
Add the things in the circles together and divide by how many circles you got.
It gives you the
average kinetic energy in the beaker. Okay? That's what it's trying to represent. Rather strange way to express it, but it's pretty effective. You'll see the same picture in your book, actually exactly the same numbers. All right. Now, they won't show the picture of the Listerine bottle. Those droplets are on the inside. Anyone know what those droplets are? If you got your book on page 105, the droplets inside the bottle. Probably not water. They could be. But if you ever tasted Listerine, or at least the old Listerine, which I guess this is, it was pretty sharp tasting because it had high quantity of alcohol in it. Alcohol actually vaporizes at a lower temperature than water does, so that's probably alcohol droplets in there. It could be water, admittedly, but my guess is, having tasted Listerine, I bet you it's alcohol droplets, or at least alcohol mixed with water. Okay.
It burns.
It surely does. That's why. Okay. Now, I think that's the only slide on evaporation and condensation. Now we're moving to 4.5 on page 106. They have a little concepts applied at the bottom, which I find sort of lame, but if you want to read it, why is it called a pop can? I doubt if that's the reason it's called pop, but it may be. It basically is saying the same thing we did in two labs ago when I had the boiling water in there and flipped it over. That's not why they call it the pop can, but that's what they're saying here. All right, now let's talk about thermodynamics. What does that word mean? Thermo means heat. Dynamic meaning changing. Things are changing, and sometimes fairly rapidly, but at least it's changing. The change of heat, the exchange, the movement of heat That's what the field of thermodynamics is. The study of heat and its relationship to mechanical and other forms of energy. Good definition for thermodynamics. Okay? The dynamic part is that relationship can be constantly changing. Thermodynamic analysis includes a whole system. Okay? For instance, I know you guys in the auto programs, you deal with the AC system, thermodynamics. Okay? You deal with the combustion system, thermodynamics. You deal with the whole system. You do deal with the individual things, but you deal with the system. You also have to deal with the surroundings of that, because in the AC system, you're letting the heat escape to the surroundings, and in your combustion system, you're making the heat escape to the surroundings through your radiator and also through the exhaust pipe as well. So your surroundings are involved as well. Now, what's going on with most thermodynamics is internal energy, that's the total internal potential and kinetic energy of the object in question, is being changed. Okay? That's going on, and that's affecting the system and the surroundings of the system. Now, several types, and here's Dimitri. Okay. Several types of energy conversions can be happening. Okay? And we've mentioned this before. If you got that car moving down the road at a pretty good speed, but then you have to change that kinetic energy really quickly, what you can friction in the brake pads, brake drums, that kind of stuff, converts mechanical energy into heat. You reduce the kinetic energy and produce a lot of heat in the braking system. Okay? And actually in the regenerative braking system, you're using that mechanical energy, the kinetic energy, to form electrical energy. You're actually generating electricity using the turning of the wheels, and that slows you down as well. Okay? I have just never read how, if there's any change of effectiveness there. Does it brake as quickly? I don't know. I haven't studied any of that. Okay, heat engines. That would be things like your internal combustion engines, the heating system in the building. Those are devices converting heat into mechanical energy. Well, not the ones in the building, but that would be your car. That's exactly what your internal combustion engine is doing. Your combusting fuel, which is stored chemical energy from eons ago, okay, little green plants out there making all that, those carbohydrates, and then the bugs that are breaking those down and making it into hydrocarbons, and that takes centuries, millennia, long periods of time for that process to go on. Stored chemical energy in your fuels is changed to heat energy as you combust those fuels, and then that heat is pushing pistons down, making mechanical energy, turning flywheels, turning axles and stuff, and that's what converts it to mechanical energy. Other applications, heat pumps. That would be more like what's going on here. You have a compressor, so you're taking electrical energy in your homes, okay, and compressing a gas, and then pumping the heat that comes from compressing that gas into your house, and that's what a heat pump does when you're heating your home. Refrigeration does the reverse of that, okay? Same as air conditioning. What you do there, you compress the gas, it starts the same thing, producing heat, but now you blow the heat to the environment, to the surroundings, and then as that gas is compressed, you blow off the heat, pump that into the house, and then let the gas expand again, and when it expands, it cools, gathering the same amount of heat that it released before. So that's what a refrigeration unit or an air conditioning unit does. Organisms, okay? I'm guessing most of you had lunch or at least breakfast or some sort of food today, and in the process you have been converting stored chemical energy in your food and those hydrocarbons and carbohydrates that you ate into energy so you can do other things. Okay? So organisms are heat machines, basically. Hurricanes. You might think they're just a terrible freak thing of nature. No, they're not. Hurricanes all happen around, they start in the tropics. Okay? Near the equator, above or below the equator, and they usually on the west coast of Africa, the ones that affect us, and they build in gathering heat from the warm waters in the summertime and bringing that heat up and distributing it into the northern latitudes. If they didn't do that, we wouldn't be able to inhabit the planet. It would be too hot around the equator and way too cold around the poles. So if the hurricanes did not move the heat, distribute the heat, we wouldn't be an inhabitable planet. So we really need to thank those hurricanes for doing that for us. Stars, including our sun, a heat machine, okay? It is having thermonuclear reactions going on constantly. Notice thermonuclear reactions going on constantly. Black holes, we don't know what they're doing, but we do know they're sucking in energy like crazy, okay? Not even light can escape a black hole. That's why they call them black holes. We don't know what's going on in there. Virtually any system with energy inputs and outputs are thermodynamic systems, okay? Now, we're going to talk about at least two laws of thermodynamics, okay? I'll mention the third one because they don't talk about it in the book, but I'll try to remember to come back and say that. First law of thermodynamics is basically conservation of energy. That's how you can summarize it. The components are the internal energy that's in the object, material, whatever you're dealing with, the heat that's either produced or absorbed, and the work that's either done by the system or done on the system. Those are the components of first law of thermodynamics. Conservation of energy basically says the energy you put in is the energy you get out. It may change forms big time, but that's what's happening. Stated in terms of changes in internal energy, and the applications are your heat engines, okay? Like your internal combustion engine. Here is one example of it. This is not a incredibly, well, I guess it does the job okay. Let's just say you have a cylinder filled with air and you put a weight on it. That weight is going to push down the piston, okay, compressing the air because it's doing work on that air. The weight, that is, you're changing the internal energy of this air by the work being done by that weight, okay? It comes to some sort of equilibrium there. Presses it enough so it holds it there. Now, you take a Bunsen burner or your spark plugs or in a diesel, the compression there that produces enough to spontaneously combust, and you add energy to this system. Now you're adding heat to the system. Now the system is doing work on the weight, pushing it upwards, and that basically equals the work that the weight did on the piston by pushing it, compressing it, okay? But here, you're producing heat. Here, heat is changing and doing work on the system. And that's exactly what goes on in an internal combustion engine. When that combustion occurs, which is actually inside the cylinder, then it forces it up. But y'all know that pretty well, okay? Now, what they should have done in my mind, let me see if they ever get around to doing it. No, they don't. Okay. They should have given you the equation for it because they number the equation that's mentioned later. Here is the conservation of energy equation in that represents the first law of thermodynamics. Now, they use some strange, I find it strange anyway, terminology for it. JQ, okay? That is the heat, okay? Now, why do they call it JQ? Okay, Q, that's what we were calling heat before, right? We did in lab, Q. They call it JQ because they convert that. We were usually using calories to measure our heat, okay? You could have used kilocalories or other things. They are saying convert that to joules. So that's what JQ stands for, the joule equivalent of that heat, okay? The joule equivalent of the heat minus the work done, there's the work part, then gives you the change of your internal energy, U2 minus U1. U1 being the initial internal energy, U2 being the final internal energy. So that's the, let's go back to this picture. To begin with, when you put the weight on here, the weight does work on the air, compressing the air, increasing its internal energy, and probably producing a little bit of heat at the same time. Not a whole lot, but mostly compressing those molecules, making them closer together, okay? Then when you add the flame, you're increasing the heat, and you're doing work on the weight, picking it up, and that also, that may be at equal internal energies, or it may have changed it somewhat. But the combination of this, the amount of heat added minus the work done, that gives you the change of internal energy. That's what they're stated in terms of changes in internal energy. That's it. So there's the first expression of the first law of thermodynamics. Now, here's how it would be related to this picture, okay? You start with a, let's say your piston, okay? High temperature region, you fire the spark plug, it explodes the gas, you have a high joule equivalent of heat here, okay? That's the JQ, high temperature region. It is going to do work on the piston, turning the shaft, all that kind of stuff. That's your work output, okay? Some of that goes to a lower temperature region. Now, this lower temperature region may not be as low as the ambient temperature. It probably isn't, okay? And this is what gets sent out the exhaust pipe, okay? But it's cooler than what it was in the piston. So some of that energy goes to work, useful work, moving, turning the crankshaft, moving the car. The others has to be expelled out the exhaust pipe. You don't want to keep it in there because it's still higher temperature. It's lower than this is, but it's so that's your change of heat minus the work, and that gives you change of internal energy. Okay, and in the internal combustion engine, probably overall internal energy stays fairly close to normal. Maybe not exactly the same, but it does happen. So this is your heat engine. You get work out from that potential difference in your heat. Okay. Now, there's another figure here, and see, they give that one, yeah, and that's going to be the heat pump. Okay, so we'll get to that one on the second law. Okay, so okay. There's one other, one more back. There's one other equation they list here, and this is when, and this is actually what's represented here. and I was saying it was probably the case. When your UL, U2 and U1, I wrote Q rather than U. Okay. When your U2 is equal to U1. In other words, you don't have a change in internal energy, which is, as I said, that's usually the case in your internal combustion engine. When you're in equilibrium there's no change, okay? So then you have the situation, if those are equal, then this is zero, right? The change of internal energy is zero. You don't have any change. Those are equal to each other. So then you have the work done. What you do, if this is equal to zero, add W to both sides. If this is zero, add W to both sides, and now you have the joule equivalent of heat is equal to the work, okay? But like I said, you're changing the temperature between the piston and the exhaust. That change of temperature there, that's equal to, this is what and here they're changing the terms a little bit on it. That's the joule equivalent of heat times the change of heat from the high region to heat in the low region. The work done is, and this is exactly what this is showing. The work that you get out of it, the energy that you get out as useful work, is the difference between the joule equivalent of heat times the difference between the heats there, okay? Because any residual that's left in here, that hasn't done any good work. It's just the difference between that and that, the joule equivalent of that gives you the work out, okay? So there's the...
Sir, could you just put some numbers on there and let's see that?
Let's see if they have any here.
Would it be, the J, would that be this number of the 40?
Okay, the J is, yes, J is 4.184 joules per calorie.
So you would multiply whatever numbers you had there.
Yeah, you see, the change of heat is usually measured in calories, or BTUs, or whatever you're measuring your heat in, okay? And then, if it's BTUs, you have a different conversion there, but you still get the conversion.
So you just subtract them and multiply them by 4.4 and give you the work.
Yeah, you see, work is usually measured in joules, heat is measured in calories, so you have to have the conversion to get you from calories to joules. Yeah, that's all that is.
I thought that's what it was.
Yeah, that's just your
Always a half a step behind it.
right. What's a little confusing, they give it the same symbol J as your unit is. Well, that's the parameter J, that's the unit joule, but it's joule equivalent of heat. They just gave it the same title. Okay?
Well, I was just thinking on the test, you probably have something on there that would have to work.
I wouldn't do any, no, well, who knows what's on the test. Okay. So there's the first law. It's basically based on conservation of energy. Okay? The energy is either used to do work or it's wasted energy. Okay? Here's the second law of thermodynamics. Now, there's three different ways you can, probably more than three, but this book gives you three. Three equivalent statements. No process can solely convert a quantity of heat to work, which that means your heat engines, your internal combustion engine, never will they be 100% efficient. Ever will they be 100% efficient. That's why the exhaust going out the exhaust pipe is hotter than ambient. That's why the heat given off by the radiator is hotter than ambient. You always have wasted heat. No process can solely convert a quantity of heat to work. In fact, your internal combustion engines at best are usually no more, I don't know, y'all made up the number, I'm going to guess around 25% efficient. I doubt if they're even that high. So much of that heat is wasted out the tailpipe, through the radiator, or just wasted heating up the air, increasing the kinetic energy of the air. Friction, okay? That's useless heat, okay? So there's one way to express it. No process can solely convert a quantity of heat to an equal quantity of work. That would be in a heat engine. Or, another way to express it, heat never flows spontaneously from cold object to hot object. It can't. It flows the other way, from hot to cold, always. That would be what you would have with refrigeration. So you have to force, the system to cool, okay? It won't do it spontaneously. You have to force it to cool. Now, almost contradicts what I said. If you have that glass of water there and it's losing some of the higher energy molecules, then it actually cools a little bit. Okay. But the water, those molecules, the molecules are actually higher energy than the surrounding is. That's what cools. Now, in your refrigeration system or in your AC system, you force the heat to blow somewhere else. In the summertime, if you have a heat pump, go out and feel the air that's being blown out of your system. Hot, hot, hot air. Now, I can remember when I was a very young child, this was a bit bizarre, we didn't have air conditioning in our house at home, so I wasn't familiar with air conditioning. But my father's older sister had air conditioning in her home. Okay, my grandmother did, and I'd just never been around a lot of air conditioning. But my aunt did, and it was just amazing to me how this machine that they had stuck in a window, it was a window unit, and it was sticking out on the front porch. Wasn't very attractive there, but that's the room she worked in. So it was sticking out there, blowing, and you could feel the hot air coming out of that, and the room was cool. I thought, wow, this is amazing. It somehow is able to take the hot air out of the room and blow it out here and blow cool air in. How does it do that? That's not what it does, okay? But that's what it seemed like to a kid. No, it didn't happen spontaneously. You were forcing that to happen. Like I said, your compressor compresses a gas, which makes it hot. If you compress something together, it's going to heat up. And these gases that they use, the refrigerants, they really heat up quickly. And what you do then with the refrigeration, blow that heat away from your system into the surrounding. That's what the air conditioner was doing, blowing it to the outside. In your refrigerator, where is it doing it? Blowing it out the back of the refrigerator. If you ever feel those coils in the back, they're hot, okay? And they have little radiator-looking veins in there to dissipate that heat. And then you take that compressed gas that you've cooled off now by blowing off the heat, move it into the condenser, I think they call it, and let it expand rapidly. Now it's sucking heat out of the environment. The environment is inside the fridge or inside the room, okay? So that's how refrigerators work. Then you take that refrigerant that's expanded again, take it back out, and compress it again, blowing the heat outside, pump it back inside, and let it do. You're doing a lot of work to make it move from cold to hot, okay? Here's the third way of expressing that. Natural processes tend toward a greater state of disorder. This is how I usually hear second law being referred to. Natural processes always tend to a greater state of disorder. Now, since many of you are a bit younger, I like to express it this way. How many of your rooms actually get neater over time? If you don't do anything to it, how many of your rooms just seem to get neater and neater all the time? Neater and neater all the time. No. I would say yes. I would say your rooms tend toward disorder. Okay? Don't they? I know mine did and do. Okay? Unless you put the energy into it to keep it neat and keep it. Everything tends to disorder. Okay? The classic example of that is take a brand new box of playing cards. Y'all are familiar with them, right? When they come in the box, they're usually in some really special order, like the ace of spades and the king of spades, the queen of spades, all the way down to the deuce of spades, then the ace of hearts, the queen of king of hearts, all the way down. Then you get to the diamonds, the ace of diamonds, and then this clubs, the ace of clubs, queen of clubs, always down to the deuce of clubs. And they're usually in that order. when you buy the cards, right? So let's imagine you did. You take them out of the box. They're in that very special order.
There's some jokers in there too.
Hey, yeah, and you probably have a few jokers in there, okay? But let's take that deck of cards and throw it into the air, okay? And you have a sheet down here on the floor so it catches them all, okay? What are the odds they're going to be in that order when they land? No, it's 0. Not going to happen. So take the sheet, 4 corners, good friends, throw them up in the air. And let's keep doing that until they get back in that order again. It's never going to happen. They just get more and more disorder. Okay? That's nature. Okay? Natural processes tend to a greater state of disorder. That state is called entropy. The entropy always increases. The state of disorder always increases. That's the second law of thermodynamics. Expressed 3 different ways. Okay, now, what are the reference scales here? Reference scales are the object's external energy. That's the energy of the global coherent motion of the object. That's associated with work. In other words, I pick up the eraser here and I throw it to somebody, okay? That is the object's external energy. The coherent thing. I did work on this and make it fly towards her, okay? I'd rather make it fly to some of these guys. Well, no, I need to throw that. No, I won't do that, okay? So that's one reference scale. The other is the object's internal energy. The total energy of the microscopic, chaotic, incoherent motion that's going on inside the object, always, okay? That's associated with heat. So you have work energy and heat energy, okay? As you add energy to a system, some of it goes to work, but some of it always goes to useless heat. Heat that you cannot recover and reuse in any way we know of. In other words, you're going to disorder. You know, things are going to disorder. You never can convert all the heat to work. Some of it just is wasted as heat. Heat never flows from the cold object to the hot object. No, hot object to the cold object can't happen. It just doesn't happen that way. Now, here's the first station. Okay, conservation of energy, the heat engine. The input energy we assume is equal to the output energy. Okay? And that is true for the total energy. For total energy. Now, is all that output energy useful work? Never. Ever. Okay? The efficiency of a heat engine is the work done per unit of input energy. So the output energy, some of it goes to work, some of it's wasted. Since there's always some waste, then the ratio of the useful work that comes out to the input that goes in, that's your efficiency of the heat engine. The second law says the efficiency is never, ever, ever 1. Like I said, the internal combustion engine, your car, at best maybe 25%. I think numbers I've seen in the past have been more like 17 to 18%. I'm just assuming they've got that efficiency up a little bit, but I doubt if it's anything past 25. I don't know. Prove me wrong. Okay? Some energy is always degraded and cannot be used for useful work. Okay? That's what the second law says, that first statement, that there's always wasted heat. Okay? And here's basically what we did in that last illustration we had, if you remember. The total energy was up here in Q high. Some of it went to work, some of it went to Q low. Q low, wasted. Work, useful work. This is never equal to that. There's always some of this, so the ratio of this to that is always less than 1. Okay? And here's what we say, efficiency is the ratio of useful work to the total input energy, QH. Okay? Okay. Oh, and here's Melanie. Okay. And for any who came in later, let me say this so everybody will have heard it, whether you go back and listen to the early part of the thing or not. Remember, next week is Thanksgiving week, and certainly Thursday and Friday are state holidays and school is closed. But there are no classes at all next week, not Monday or Tuesday or Wednesday. We have professional meetings either down in Mobile for some of them or on the Birmingham West Campus for the rest of us. We have professional meetings Monday and Tuesday. Wednesdays are just office days, or at least that's what they say they're going to be. I hope they are, so I can get some work done. Okay? The other is this. Never mind, I didn't say that. Okay. Yes, it'll never be one. Okay. Because there's always wasted meeting time. Oh, did I say that? Okay. Never mind. Can't remember if there's one more slide on the same one or not. I'll let you get all this written before.
Oh, I did.
Huh? Got it? Everybody got it? Let's see. Nope, it went to a new slide. Okay. So the efficiency is always less than 1. Okay? Usually by a big amount. Okay? Now, one of the most efficient machines, and I bet you a lot of you have done these, hydraulic devices. Okay? Hydraulic pumps or lifts or things like this. Boy, those fluids transmit and do the work. I can't say with no excess heat. Anytime you compress anything, it's going to give off a little bit of heat. Boy, a hydraulic lift or something like that, very, very efficient. I would say probably pretty close to 90% efficient, or maybe even higher. Okay, heat engines are notoriously bad. Okay. All right. So here's the second statement of the second law. Conservation of energy. Again, this shows. This is sort of a reverse of what we showed before. In this case, you're doing work to a system, and so your input is here, and you're creating heat. Okay. In other words, your compressor is doing the work. It's compressing that gas, compressing that so that it heats up. Okay. Now it's taking the gas that was at, say, low temperature region and compressing it and putting it into a higher energy region, okay, higher temperature region. You're blowing that temperature into your house, okay? Now, work is required to move the energy from the cold region to the hot region. It happens. This is the same thing of cleaning your room. Work is required to make it get back to a state of more order, okay? So work is required, okay? Energy arriving at the high temperature region is energy from the low temperature region, plus the work needed to move it to the high energy. Upgrading of energy by the heat pump is accompanied by greater degradation of energy elsewhere. In other words, what was creating the work, okay? What was making it happen? Now here's sort of a dumb example of it, but I think it's pretty appropriate. If you've ever had the AC go out on a really hot summer day, and say you're in the kitchen and you think, oh, we need to get a little cool in here, and you can't open the windows or something like that. Have you ever been tempted to open the refrigerator door and say, let's cool off the room by opening the refrigerator door? And stick your head in, yeah. Will that cool your room? No, it heats your room. Why? Okay.
It cools me off.
Okay, it cools you off, but it will not cool the room. Because you open that door, the cool that's in there, now the unit starts running, it's using electrical energy that's input, turning the turbine, the compressor. The compressor compresses the gas, and then the fan at the back is blowing it into the room, heat into the room. And sure enough, you do cool off the room, okay? Cool off the refrigerator, but you're heating up the room. So actually, all that electrical energy you're using to run that is now producing heat that is actually going to raise the temperature of the room. Yeah, you stick your head in, you feel cooler there, but the room is going to be getting warmer. Very slowly, very slightly, but you see there's always a, as it says here, accompanied by greater degradation elsewhere. That was the electrical energy compressing the gas in your refrigeration system and blowing that heat into the room, okay, out the back of the refrigerator. Yes?
What if we turn off the refrigerator?
If what?
Turn off the refrigerator.
Okay? All right. Now, that would be the equivalent to bringing in a block of ice, wouldn't it? Okay? Right? Yeah. That will tend to cool the room a little bit, but the average at the end of the room and refrigerator is going to be probably warmer than the average was at the beginning, or at least no cooler. Okay? Because the refrigerator was already cold inside. You open it up, it warms up, the room cools off a little bit. Okay? Yeah. If you don't have the electricity going in, your compressor's not going to work. Yeah, it's not going to produce any additional heat. But it's not going to get the overall energy of the room, system, and environment is going to stay constant. But it won't get any less. Ever. It will not ever get less. The room may get less, but the overall, no. Okay.
Quick question.
I'm sorry?
Quick question. If we don't have time,
Sure.
don't answer this. If we don't have time, don't answer this. But I was wondering about heat pump system.
Heat pumps?
Cools one out and heats one out.
Yes. Okay. What?
But on that up there, that's heating only.
Okay.
That's a heat pump itself.
Okay. A heat pump on the heating mode, this is going into your house. Okay? In the cooling mode, this is going into your house. You pump that to the outside and pump this in. Okay?
Well, they're pretty efficient.
Yeah, and they are
Now,
fairly
as it
efficient.
used to be, but they are now.
Yeah, they're much better than they used to be. The furnaces are more efficient than they used to be. I'm sure the automobiles are too, but they never get to one. You know, always as long as second law of thermodynamics. Everything tends to disorder. Okay. Here's the third statement, still on the second law. Real processes are irreversible processes. Okay? Now, what does that mean when you do something like heating that gas in the compressor? Okay? Blowing the heat away, you'll always have some excess heat, more than just the cooling when you let it expand again. Because guess what? You used energy to compress it. So the amount of cooling you get here is not equal to that. You're blowing more heat into the room than you've extracted from it because you used energy to compress it. Okay? It wasn't a zero-sum game. Okay? They're never irreversible processes. The measure of disorder is called the entropy. In these terms, the total entropy of the universe is continuing to increase, okay, which means that you're going to more and more disorder. Now, this smacks into the face of one of the pretty popular theories, at least in some people it's a pretty popular theory, and that's the theory of evolution. Wait a minute. The whole theory of evolution requires that things be going to greater order. That things started off just a few little microbes here, and then they combined into a system and evolved into higher and higher order things. Okay. Ooh, that would be saying that things tend to greater order, whereas the second law says they go to more disorder.
So by what you're saying, you don't buy that?
But
You don't have to answer.
yeah, here's the thing. Energy is being input as for instance, an athlete strengthens his muscle, okay, going to greater degrees of efficiency, you might say. But it's taking a lot of work to get there, okay? So The overall system, no. Now, I think species can adapt and in that sense evolve, okay, to changes in their environment. You know they do.
Polar bears really warm.
Yeah. But I was thinking there is some type of a bird. I can't think of what kind of. No, it may not be a bird. No, it's a moth. It's a moth. That it has changed its color over time. It loved to sit on the edge of a building. And when they built a bunch of brand new limestone or buildings in, say, England, this is where they studied it. I believe it was anyway. And Stephanie is here. Okay. All these, when Britain was becoming a big world power, they started building with marble and limestone and light-colored buildings. And this moth, who liked to live on the buildings, it adjusted to be lighter in color. Now, they think the reason for that, the darker moths were eaten by predators, and the ones who inherited the lighter genes, they became lighter, and because that's how they survived. But then, when Britain sort of went into a period of not doing quite as well, they didn't keep those buildings sandblasted and cleaned as much. So now the buildings got mold on them and they turned grayer. The moths turned around and became grayer again. So they did evolve, they did change, and natural selection was part of that and other things were. So yes, things do change, but boy, can the evolution jump up huge levels. That's where I'm not sure. I can't. The trouble is, it's a theory. You can't go back and test it and say, well, can I make these two molecules become something else? No, that took an awful long time. So I don't know. I don't want to get into it. Okay, I did. Okay. Natural processes degrade coherent, useful energy. That's what they mean here. Natural process degrade coherent, useful energy. Some of it always winds up going to incoherent, unuseful energy. Heat, basically. Okay? Available energy of the universe is diminishing. Okay? Eventually, the universe will die a heat death, at least according to this. And again, this is they say it's a law, it's still sort of a theory. We can't test this. We don't have the one universe to live in, so we don't know if it's actually going to die or not. If it does, we won't be around to say, hey, I told you so, because we'll be dead. Okay. The direction of natural processes always moves toward more disorder. Here's their example. I gave you one of the deck of cards. Here's one. You spill milk. Can you ever unspill it and get it back into the glass? Never. Okay? You cannot do that. If you could do it, it's going to take an awful lot of work to do it. Okay? If you could suck it up and get it to go back into the glass, it would take a lot of work to make that happen. So you'll always have loss. Only way to get more order is to do a lot of work to make it more order. Yes?
What is ENTROP?
Entropy?
I'm not familiar.
This right here? Entropy, is that what you're asking?
What does that mean?
It means a state of disorder. The entropy of a system, state of disorder. Technically, it has a name that involves a partial derivative. That probably wouldn't make.
Right.
Yeah. Okay. Entropy. Yeah. State of disorder. And let me get print here. Okay. Anyone else come in that I wasn't looking? Okay. And here is.
I was already here.
Oh, you're already been here. Yeah, that's what I'm thinking. Oh, yeah, I already got you here. Okay. All right. Everybody got this now? Okay. That's the last slide in the chapter. Okay. There's some mistakes and misunderstandings at the bottom of page 108. This one's probably a little bit better than some. but it's not all that great. Have you ever heard someone propose a perpetual motion machine? It's not going to happen. Second law of thermodynamics said it can't happen. Okay? So I'll let you read that. There is a guy mentioned here in People Behind the Science of Count Rumford. Okay? His real name was Benjamin Thompson. And he is a very interesting story in himself. Notice the years that he lived. 1753 to 1814. What happened in that time frame of his lifetime? 1753 to 1814. Say again? No, that was before Emancipation Proclamation. That was 1850s, 60s. Yeah. Okay. You're pretty close. In our U.S. history, what happened?
Independence.
Independence, yes. We became independent from Britain then. Okay? Now, here's a little background on William Thompson. He was living in, I believe, upstate New York. No, Massachusetts. Okay? Or born in Massachusetts. Okay? But he and a lot of the early independence seekers, like the Adams brothers, Samuel and John Adams and those others, there was a firestorm in Massachusetts. They really wanted their independence. William Thompson wanted to remain a British citizen. He didn't want to be independent from Britain. He thought we were better off as British citizens. So he did not support our War of Independence. In fact, some people have suggested that he probably was cohorted a little bit with Benedict Arnold, perhaps. Okay? Benedict Arnold got caught and I believe executed, didn't he? For being a traitor?
Who?
Benedict Arnold. Oh, y'all don't know your history, do you? Okay.
Yeah, he was a traitor.
Yeah, he was. I can't remember if he actually got executed or he got sent to England or what. But anyway, William Thompson got out of town in time, and he went to England. And because he supported the British cause, he was made a count. It's a low-level royalty, but that's why he was called Count Rumford. He wasn't born to royalty. They made him one. But what he was an engineer. And this was about the time when, you remember what the weapons were in our independence, muskets instead of rifles, but they did have cannon, okay? And he was an engineer, and he could make some pretty good cannon. So he was doing this, actually mercenary, doing it for the Germans, not the British, but the Germans. He was hired by the Germans to make them cannon. I think he was doing this pretty near Munich or somewhere like that. And he noticed that when what they did at the time, they poured slag iron, basically a lot like cast iron, into a mold, and then they drilled out the bore of the cannon. Not a very efficient process, but that's how they did it. Poured the whole cannon barrel and then drilled out the hole, and then did the mechanisms and stuff like that. We noticed when his bits got old, they wouldn't bore very well, and he noticed that the material got pretty hot. He said, wait a minute, because before this, heat was considered an ephemeral substance that lived inside a material. It was counted an element. It was not counted to do anything with energy or work. He said, look, it has to be. So what he did, he took a defective cannon thing that he wasn't going to use, took his oldest, dullest bit, and he already had started a hole there, and it had cracked and done something. So what he decided to do was get it going, and he put ice. He was fairly close to the Alps, brought down ice, filled the cannon with that hole that he had there, he had a horse walking around in circles, that's what turned the bit, and within an hour he had that ice boiling because the bit was so dull. And he said, look, this heat, and he could produce as much heat as he wanted to. He said the heat is not a material part of the iron or the water or the snow or anything else. The heat is produced by work. That is the first indication that heat was actually a form of energy, not some element inside a material. He was the one who discovered that. Trader though he was, he was a pretty sharp dude. Now don't confuse him with William Thomson. That Thomson doesn't have a P in it. He was Lord Kelvin. Also, he was actually British, and he was a real lord. I mean, high up there, aristocracy. He was a great physicist also. He's the one that came up with the 3 laws of thermodynamics. So don't confuse the two Thomson. One's a Thomson, other's a Thomson. Okay. So anyway, you wanted some numbers. I meant to do this. I knew that was in here somewhere, but I couldn't remember where. Let's go back to here. Okay. Example 4.8. A heat engine operates with 65 kilocalories of heat supplied. 65.0 kilocalories of heat supplied. That would be your QH, I believe. Yes. Exhausts 40 kilocalories of heat. 40.0 kilocalories. That's your QL. The low energy heat that you can't use. That's your exhaust. Okay? How much work did the engine do?
15 times that 4 point.
Second?
Is it 15 times 4 point? What is that number?
Okay. Where'd you get 15? 25? 65 to 40.
45 times 4.165 or whatever that number is.
Right. Okay, but it's 25.
Yeah.
Okay, I thought you said 15. Okay. Okay, yeah. Yeah. So you take the difference of these two, and that's 25.0 kilocalories, okay, of work that you did. This would be your work. Now change that, you're absolutely right, to joules, okay, because you usually measure work in joules. Now, since you're dealing with kilocalories here, you would multiply this by 4. Goodness, I'll never remember that number. 4.184. And that would be kilojoules per kilocalorie. Okay? Is that the way it goes? Yeah. Kilojoules per kilocalorie. They use 4,184 joules. That's fine, but why not use kilojoules, okay? And multiply that. So if someone has a calculator, 25 times 4.184. Anybody? $25 times 4.184. Say again? 104.6 joules of work. That's the work that you did. Okay? They're going to round that to 105 because you only have 3 significant digits. That would be your useful work. Okay? Now, what they didn't ask for, what's the efficiency of that engine? Don't deal with the 105. Go back to this. That would be 25.0 kilocalories of work divided by 65.0 kilocalories of input. See what that comes out being. Not 1. Nowhere close to 1. What do you get? 0.3? Second? 0.4? 0.4, or 40%. That's your efficiency of that engine, whatever it happened to be. Okay. So I don't know if that's what you meant by some numbers, but that's, yeah.
Excuse me, so that means we divide 25.0 by
Yeah.
4.
Efficiency is the amount of useful work done divided by the total energy put in.
So, I'm sorry, so that means we just divide 25.0 by 4.18.
No. Okay. The 4.184, that was what got you from kilocalories to joules. That's all it did, was change your units from a heat unit to a work unit. That's the only thing you did there. When you're getting efficiency, keep the same units, kilocalories, the units of kilocalories of work done divided by the kilocalorie of energy input.
So that means that's
184, multiply it by the 25 kilocalories, and that gives you 104 joules.
That means I have to also divide this by this.
Okay, now the dividing is a separate thing. I just said, by the way, this is part of the problem. What is the efficiency of this engine? Will you take this divided by that? That was a separate issue, completely. Okay, good deal. All right. What's that? No, it isn't. All right, that does end the chapter. There's thermodynamics in action. You can read that. It's a pretty good little thing. And as you hear me say every chapter, nothing replaces reading the chapter. Please read the chapter. Once you've read it, then the summary kind of highlights some of the most important issues. Basically, the things they put in italics are things to really pay attention to. There's a summary of equations. There were 8 of them in this chapter. I would pay attention to those. You might want to put those on your formula and equation sheet. That's up to you. Key terms here, probably a few fewer than most, but they're listed alphabetically, but they give the page numbers where that key term was either first defined or mentioned. But then the applying the concepts, there's 43 questions there, multiple choice all, with the answers given at the end. If you can do those and get those right, practice on those, you'll probably, if there's any that you say, I don't see how they got that, bring those to class, okay? But if you did get those, you'll have most of the key ideas of the chapter down. There's also questions for thought. This is about normal number here, about 17 of those. For further analysis, maybe a few more than normal, 7, okay? And then there's an invitation to inquiry. You can look at that if you'd like to. The parallel exercises are more like the examples we did through the chapter. If you have the big book, I know they have the answers in the back. I don't know if the little ones do. I never have found it there, but I don't have one of the little books. I don't know. Group A did have answers in the back. Group B did not. All right, and again, we are skipping chapter 5 if you have a big book. And your book probably goes straight to chapter 6, right? So chapter 6 begins on page 140. So let me get out of here and discard this and this and that and go to chapter 6. Now, it's coming up. How are we doing on time? 4:45. We've only got 30 more minutes of class. No, we have an hour more of class. That's good. An hour more of class. So we should be able to get far enough here to get most of the lab covered. All right. So let's start the slideshow here. All right. Now the title of this chapter, they say here, is electricity. The actual title should be electricity and magnetism, because the first part of the chapter is electricity, the second part is magnetism. And guess what? Those are connected. Believe it or not, those are related to each other. Notice several people have been having to go. Do y'all need to take a little break? Yes? Okay. All right. Any of the others want to take? It's a good break place. Do y'all need to take a break? Yes? Okay. So we'll hold off here. Try to get back in 5 minutes or less. I would say less if at all possible. So I'm going to pause. All right. This chapter is, like I said, I prefer to call it electricity and magnetism because we talk about both of them in the chapter. They entitle it just electricity because they are related. Now there's a lightning strike, a pretty incredible picture showing lightning coming down, and it seems like a pretty good storm all over the place. I think, I can't tell, this looks like it's water down here, so that's reflecting other lightning. I don't know, you can't see the other, but it's a pretty impressive picture, okay? And what I imagine that, I don't know if everybody realizes, where does lightning come from and to?
From the sky.
Okay, that's what most people think, and most of it does, from the sky to the earth. But not all of it.
Cloud collide.
Yes, you have cloud-to-cloud lightning as well. But
Really go from the ground up.
there is also lightning that goes from ground up. And this isn't a picture of that, but there have been pictures taken that just happen to be snapping at the very time that happened, and you'll see it going up and just ending somewhere in the middle of the sky because it's going ground to
I
ground.
was told that years ago, but I still don't believe it.
Right. And so it's pretty incredible.
What about
We'll be talking about that a little bit later, okay? So let's talk the core concept here, which is on your page 140. And notice the core concept has both of them. Electric and magnetic fields interact and can produce forces. They do produce forces, okay? So that's your core concept here. So the chapter should be titled Electricity and Magnetism because we're going to be talking about both. It's sort of like you can't have one without the other, okay? So what are the concepts of electricity? Now, a lot of what we say here, we're going to say again in chapter 8, which is the next chapter we do, so sort of hang on to it. You think we're just repeating, but they're important in different ways. Let's start out with the electron theory of charge. Way back in time, okay, people knew about electricity, but nothing useful. In fact, about the extent of it, it was a parlor game. Someone would get a piece of amber, which is basically fossilized resin from wood or something like this, and they would take that and rub it with fur, I think it was, or wool, either one, that's sort of like fur. Rub it with there and sneak up behind their friend and touch them with it and give them a shock. That's about the extent that anyone knew of electricity. They knew if you rubbed amber with wool or with fur, you're going to build up a charge. They didn't know it was a charge, and you could shock people. Nothing harmful, just really amazing, but it happened. Now you're here, see some of these same names again in the next chapter. In fact, mixed in with a lot more. J.J. Thomson identified what was actually the charged particles that were being moved around there, and those were called electrons. Now, he didn't say that they were negative. That was actually done by an American statesman, Benjamin Franklin. Actually was the one who decided some charges are positive, some charges are negative. He gave those titles, and it happened to be the electrons wound up being negative, which is too bad because it really messes up the way we talk about electricity. Not in a bad sense. Well, here is where this concept comes from. The basic concept is the basic unit of matter is an atom. Now, what we mean by that is if you have a piece of iron and break it into smaller and 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 smaller pieces, you can only get down, and no one can actually do this, with the smallest piece of iron that you could have to still be iron, that you couldn't break it apart and still be iron, would be an atom of iron. Now, this was a concept that came up in the ancient Greeks. Democritus was one who came up with this, and it was named atom because he said it was indivisible. It can't be gotten any smaller than that. A few generations later, here came Aristotle, who was the big honcho. He said, no, matter is a continuum, it'll always be iron. You can't break it into any small piece. So he threw out Democritus' idea of atom. Well, much later, we had to bring it back in when we saw other things happening and said, no, there has to be a smallest piece. What are the atoms made of? They are made out of smaller particles, but they won't be iron anymore. The atom is made up of, I like to start with the nuclei. The nuclei is a collection of two things, protons and or neutrons. I have to have protons. There's one that doesn't have a neutron, that's hydrogen. Most of the time doesn't have a neutron, but every other one has neutrons as well. So protons and neutrons, they are the bulk of the mass of an atom is in those protons and neutrons. I mean, 99.99999% of the mass is in that nucleus. Maybe not quite that many nines, but awful close to it. Okay? And those are all in the protons and neutrons. Now, what are the protons? Protons, P, positively charged. Neutron, neutral, no charge. Okay? The electrons have the negative charge. So don't think the N for neutron means negative. It doesn't. The negative charge is in the electron. But now electrons have hardly any mass at all. I mean, just like 1/10,000th of the mass of a proton and neutron. And they fly around in this cloud surrounding that nucleus. Okay? Now this isn't quite to scale. If this was to scale, that dot would be just so ever so tiny, and the electron cloud would be much bigger. But all the mass is in that tiny little dot in the middle, and hardly any mass is in that cloud of electrons. My brother came home from Georgia Tech, his probably sophomore year. He said, most of everything is nothing, and that's really true, because most of the volume of every atom is absolute void space. Most of the mass, in fact, almost all the mass is in a tiny little nucleus surrounded by a cloud of electrons that have absolutely hardly any mass, surrounded by nothing. Okay? So most of everything is nothing. Okay? So here's your electron clouds, and that's all it is. It's just a few electrons. Okay, in fact, this one happens to be helium. 2 protons, 2 neutrons. That makes a helium nucleus. So that means there's 2 electrons flying around here. And they're basically in they make it look like there's an inner ring and an outer ring. They're basically all in a ring. That's what makes helium. Okay? All the mass is concentrated in that tiny little nucleus, and the cloud of electrons that takes up most of the volume, just about all the volume, is just these little, almost massless electrons that are negatively charged, but flying through space, just wandering around there. Okay? Chapter 8 will go into more detail on that. Okay. What is the electric charge? Well, this really massive proton has a 1+ charge, and this almost massless electron has 1 negative charge. You can't break the charge any smaller than that. 1 positive or 1 negative. Electron represents the smallest unit of charge you can possibly have, a negative charge. Okay. Hang on to that concept that the protons are positively charged, but they don't move. Only the electrons move. Okay. So the charges in matter are inseparable property of certain particles, as in protons or electrons. The electrons have a negative electric charge, protons have a positive electric charge. So there is a charge interaction here, and that charge interaction produces the electric force. Okay? We'll get back to that in a minute. Here's the rule. Like charges repel each other, unlike charges attract each other. Okay? Now,
Go ahead, man.
what's that?
Let's just absorb what you said. Like particles.
Repel each other, and unlike charges attract each other. Positive attracts negative. Huh?
The opposite of a magnet.
No. Like poles of a magnet. A north pole will deviate from another north pole that will be attracted to the south pole.
Okay.
Yeah, same type thing. We'll do that later, and we'll get there. Okay. Now, they bring up another term here. An atom is always, by definition, neutral. Neutral charge. Same number of electrons as protons. Always. But those electrons flying around in that cloud, it's real easy for one of those to sneak off or for it to grab another. That's a cloud out there. If it either grabs an extra electron or loses an electron, then it becomes an ion. An ion is a non-zero net charge. either from losing or gaining electrons. Do you ever gain or lose protons? Never, okay? Because that would be a nuclear reaction, a very major nuclear reaction. We hope that doesn't happen, okay? The only way you become a negative ion is to gain an electron. The only way to become a positive ion is to lose an electron. It's always the electrons that are gained or lost, okay? Never protons.
So, like, whenever they talk about splitting an atom, they just mean the nuclei of an atom.
Okay, yeah. Now, when you have atomic reaction, that's splitting. It's either splitting or fusing nuclei together. That's nuclear power. We're not going there. We're in electricity and magnetism. Electricity and magnetism does not mess with the nucleus. It stays intact always in electric issues. Okay. Now here is a sample, and they're going to use this for various purposes. Some of it not quite correctly, but this is okay. This shows 3 positive charges. What it doesn't show is the neutrons. It probably has at least 3 neutrons in there too. Don't worry about that. We're not using it. And then it shows 3 negative charges. These are your electrons. Now the size is way out of proportion. If this was proportional, this would be a tiny little pixel in the middle, and these would be a great big cloud out here. But it only contains 3 protons, 3 electrons. Now this part is correct. 2 of those electrons are what we call an inner shell, and then the third one leftover electron out here is by itself in an outer shell. Electrons don't like to be by themselves. They like to be with other electrons. So this electron is really easy to go. Easy to be lost. That's going to make a net positive charge. This, by the way, if this is 3 protons, 3 electrons, that would be lithium. Not a very common material, but that would be lithium. They're not focusing on that right now. But if that were to lose an electron, it would no longer be an atom of lithium. It would be an ion, lithium ion, a positive ion of lithium. And that does happen, by the way, because it likes this is happy to be like it is, but this one is real happy to go. Okay? Electrically, it's not happy, but just to satisfy its need to be with others, it wants to go. And that's what it shows here. If it were to lose an electron, which it does, lithium is easy to lose an electron. That electron is moved. Now it becomes a positive ion because it has 3 pluses and only 2 minuses. So that becomes a positive lithium ion, which does happen in nature very frequently. In fact, most lithium you'll see will have done this and become a lithium ion before. Lithium doesn't exist as a element very frequently in nature. Not very frequent anyway, but it certainly doesn't do that. Okay? Now this is the one that doesn't happen. Lithium doesn't pick up a second electron. It just doesn't happen. Okay? Chemically, that's not a feasible interaction to be doing. Now, but they didn't want to do a new figure here. If we had gone across the periodic table, and you do have a periodic table hopefully somewhere in the back of your book, if nowhere else in chapter 8, but I think you do somewhere in the back of the book. You go all the way across from lithium, don't go as far as neon, but go to fluorine. Fluorine has 9, and we'll get to this in chapter 8, it has 9 protons. That's what the 9 up there is for. It's called the atomic number. That means neutral fluorine has 9 electrons. Okay? And here's how those 9 electrons, 2 are in the inner shell, and then you have a pair here, this was in 3 dimensions, but a pair, that would be 4, another pair, 6, another pair, 8, and one more, 9. That's how it sort of divides up. This one that's by itself doesn't like being by itself. It loves to rip off an electron from somewhere else. Like maybe a lithium. Grab that electron that was all by itself there, bring it in here, now it's happy to be with that, paired with that. Now fluorine would be a negatively charged ion. Okay. Fluorine doesn't lose electrons, it steals electrons. Lithium doesn't gain electrons, it loses electrons. But that's not what they're focusing on now. any atom that picks up an extra electron, this one wouldn't happen, but if it did, it would become a negatively charged atom. And that's what it's trying to show, a negative ion, one that an electron has been added. They just didn't want to go to a new graphic and show it with 9 in there. 9 pluses, you wouldn't be able to count them all. 2 electrons and then 7 in the outer shell. It loves having 8 in the outer shell. Okay. So, but that would be, if it picked up one, it would be a negative ion. It just doesn't happen. Now, what is static electricity? What does static mean to you? Think of another word that starts with S-T-A-T-I. Something like stationary? Okay, yeah, okay. Something like that. It's fixed. Static electricity is just when you exchange charges, but they just stay in place. Okay? And we call that an electrostatic charge. You add electrons or delete electrons, one way or another, but it stays in place. Stationary charge confined to an object. That's what happened when you rub the amber with fur or with wool. You were knocking electrons off the wool onto the amber. So now you had excess electrons there, sneak up behind your friend and shock them. Yeah, a lot of fun. Okay? Get old pretty quickly. Okay? But that's what was happening. That's called electrostatic charge. What's the charging mechanism? Rubbing the amber with the fur, that's friction, knocking charges off one onto another. Or, and by the way, that's what's happening with clouds. The clouds moving around out there, a thunderstorm happening, clouds moving around, knock electrons off one cloud onto another cloud. This one builds up negative charge, this one builds up positive charge, and if that charge difference is large enough, discharge lightning. Or if this negative one,
Wait a minute, you just went from
cloud to cloud. Cloud to cloud.
Right.
Now, if you had this negative charge cloud near the ground, which happens with a thunderstorm, the clouds get pretty low.
Heat lightning.
Okay, heat lightning is just lightning. Clouds are moving around because of heat. When they rub electrons off, that's the same thing. It's an electron unbalanced charge. Now, if this positive cloud up here was the one that was down here, and it got too close to Earth, it's pulling electrons off the Earth. The Earth has plenty of electrons, and because if the potential differences are great enough, we'll get to that later, then you have ground to cloud light. Okay, that's all that's right. So, now, second way, contact with a charged object. Okay? Now, when I was working in radon research for Southern Research Institute, we had the projects that we did down in Florida. That's why we're doing in Florida. In Polk County, that's where Lakeland and Bartow are. They do a lot of phosphate mining there. And when that phosphate mining happens, they tend to have higher levels of radon gas from the residue from the phosphate mining. And houses are built on that residue, and they get excess radon. So we would usually stay at fairly cheap motels because we were using research dollars to do that, so we tried to find as cheap as possible. And they usually have this polyester carpeting, and you walk across those with, say, rubber soles or something like that, and what you're doing is getting electrons off the polyester onto the rubber or vice versa, probably that way. And then you reach for your doorknob, which back then was all metal, and when you actually had doorknobs, okay, and you sometimes get a shock, okay? Now, I bet you some of you, if you're old enough, there used to be some seat covers that were made out of cheap plastic. You scoot across them with cotton clothing on and reach the door handle and get a shock, okay? It happens all the time. That was all examples of static electricity. That's caused by friction. Well, if you didn't want to get shocked, then pull out your room key. That's back when they had room keys and not cards anymore. Y'all probably don't remember this. Pull out the room key. You hold the key. You now transfer the extra charge you picked up to the key. You hold it up near the door. You could actually at night see the spark there. You wouldn't feel shocked because you transferred it, because you were in touch with a the key was in touch with the charged object, U. Now it becomes charged. Okay? Now there's another thing that happens, and this is called polarization. Now there's really several things that we call polarization. They're all related. But I don't know, you may have seen this demonstrated before. You have a rubberized comb, rubber comb, and you comb your hair. Now here's what's required. Your hair needs to be fairly clean, where you have to have enough hair to comb, but that's beside the point. But if you have enough hair, and your hair is fairly clean, and it's fairly dry, not your hair, but the temperature and the humidity. Your hair needs to be dry too. Comb your hair, and then if you had a little stack of shreds of paper here, and hold the comb near it, it'll pick up pieces of paper.
Will it not make your hair stand?
And also, you can, if it's a dry day and you're combing your hair, sometimes your hair, rather than getting into place, follows the comb when you leave. Same principle. And I think there's a picture of a gal doing that in the book. So, same type thing. That's polarization. Well, here's the polarization. You're actually friction of the comb on your hair, that's making the comb negatively charged. It knocked the electrons off your hair onto the comb. So it's negatively charged. You hold it down near those pieces of paper, little shreds of paper that you tore up into tiny little pieces. Well, the first one of those that it gets close to, that's neutral. The paper's neutral. Not reason it to be charged. But the electrons in the paper, because the comb has excess electrons, the electrons closest on the piece of paper closest, they get away because the like charges repel each other. That leaves positive sites on the paper. It's now attracted to the comb. But then the next piece of paper, because the electrons are going to that side, it attracts the next group. That's polarization. A reorientation of induced charges without changing the net charge. Those pieces of paper become positive this way, negative this way. Then this one becomes positive this way, negative that way. And you can have a string of them, to some extent. Now, my wife would shoot me for saying this, but in our house, we have a fair number of cobwebs. What in the world are cobwebs? Second? From little cob spiders, you think? No, that's not what they are. They're actually little dust particles.
They're dust bunnies.
Yeah, they're dust bunnies hanging because little colloidal, meaning tiny little particles of dust, are usually slightly charged, and they will induce a charge on the next one, on the next one, on the next one. They're just a string of charges. Because you reach up and touch it, they're not sticky like a spider web. They just dissipate completely into thin air almost, or you get a little bit of dust on your hands. That's what a cobweb is. It's not really a web. It looks like a web, but it really isn't. It's polarized dust particles stuck one to another to another to another. Okay? Now, here's the gal combing her hair. Rubber comb, hair has to be dry and clean, and because a little bit of oil on it, it's not going to do as well. But if it's clean and dry, and the air is fairly dry, you comb the hair, you knock electrons off the hair onto the comb. Before you comb, balance charges. Positive here, negatives here, positive, negative. Same number of charges. Everything's neutral. Comb the hair, and now you knock negative electrons off the hair onto the comb, and then you pull the comb away, and it attracts the positive, and your hair gets messier because it's falling. You've never had that happen, have you? Okay. It probably does. Okay. And also, in doing that, now the hair being net positive now, the hair try to get further away from each other because they're same charge, and they try to repel each other. Okay? And follow the comb, which is negative. So actually the hair looks worse, and she looks really upset about it. So that's from friction. Okay? Here is what I was talking about with the polarization. Hold that negatively charged comb near the piece of paper. Now they're usually much more ragged than this. And this polarizes the charges here, attracting the positive charges, called unlike charges attract, and repelling the negative charges. They get on the next one down. And so now this becomes polarized. positive up this way, negative down that way. If you have another piece of paper here, it gets polarized, positive up, negative down, and they make a chain of them until you can't hold them. After a while, they won't hold together anymore, but that's exactly what the dust particles do in a cobweb. They just chain onto each other, either polarized or because they're slightly charged themselves. Okay? That's all static electricity. Now, let me make sure I'm not missing anything here. There's a little science sketch there. If you want us to read that, you can. There's a gal combing her hair, all that. Static charges, concepts applied there. You can try that if you'd like to. Okay? Now, we're moving into electrical conductors and insulators, which is at the bottom of page 143 onto the top of the next page. Now, some materials conduct electricity really nicely, really easily. Others do not. Those that conduct it well, we call electrical conductors. Now, if you remember back in the last chapter, chapter 4, we talked about the conductivity of heat. And heat, some materials conduct heat well, and some do not. Some are good conductors of heat, some are good insulators. Remember the metal rod and the plastic rod. Hold against your cheek, okay? Metal was a great conductor. Plastic was not a good conductor. It was an insulator, okay? You have the same thing with electrical. In fact, most of the materials are similar. A good heat conductor is usually a good electrical conductor. Metal's a good electrical conductor, plastic is not, okay? Now, what makes an electrical conductor a good conductor? What is carrying the charge? Electrons. Those are the charged particles in nature. Protons are also charged, but they don't move. It's the electrons that move. If the material has free electrons to move throughout the material, it makes a good conductor. And guess what? Most of your metals have those free electrons, especially what they call the transition metals, which are in the middle of your periodic table here. These are called the transition elements, and most of them are metals. The blues are all metals, and those are good conductors in general. Okay? Most of the stuff out here and here, not as good. Okay? Now, if you have a good conductor, like that key was, remember I said when you have that static charge, you hold the key transmits the charges really easily. So if you're holding it, the charges move right through you to the key, and then they discharge through the air, and you got near the metal door frame. Okay? The added charge dissipates real quickly. Examples are metals, which include graphite, which is not a metal, okay? It's a certain form of carbon. Carbon is not considered a metal, and it's not usually a good conductor unless it's graphite. That's the way graphite is put together in a two-dimensional sheet. It has exposed electrons. The electrons can move very easily from one to another, okay? Your good electrical insulators, the electron motions are restricted. They're either great big old molecules that hold those electrons really tightly. And by the way, there's two types of bonding. There's more than two, but two main types of bonding of compounds. You have ionic bonding, which is exchanging electrons, or covalent bonding, which is sharing electrons. Those covalent bonds, they don't have free electrons. The ionic bonds, they have a bit more free electrons. So that's sort of a difference there. The electron motions are restricted when they're shared electrons. The added charge tends to remain on the object, and examples of this are glass, a good insulator, a bad conductor, wood. Now they talk about dry wood here, not wet wood. You get water on wood, it makes a good conductor. Diamond, which is pure carbon just like graphite is, but that's a three-dimensional structure. All the electrons are tied up and holding each other together. There's a lot of difference between graphite and carbon and diamond, even though they're identically chemically. Yeah.
Spark plug wires.
Second.
Spark plug wires, some of these guys do.
Yeah.
You know,
Yeah.
are they graphite?
I guess they could be. Does anyone know?
Well, it used to be.
I know that pole is. I think the pole is graphite, isn't it? The thing that sticks up, there's a piece of metal that goes like this.
And they're not metal.
Yeah. Right. It could be graphite. I don't know. And I think that you know what I'm talking about in the spark plug. There's a pole that sticks up. It's usually
No,
dark.
The whole wire, because I'm metal.
No, graphite would be too, ready to break. It's a copper wire,
Yeah, that's what. Oh, you mean the wire? Okay, I'm sorry. I thought you meant that pole that's there.
No, I'm talking about the wire.
The wire.
Yeah.
I don't know.
Because it's not like a copper wire, maybe like from the 50s.
Yeah.
Okay.
I don't know
Just
the answer to
forget
this.
that.
Those guys will know better than me. Okay. But graphite, what's another thing it's used for? A lubricant.
What?
Graphite is used as a lubricant.
Oh.
Right? It's real slick stuff. Okay. Think of soot in your chimney. Have you ever handled any? That's just as slick as snot. I mean, it's slick. Okay. All right.
Pencil lead.
Huh?
Pencil lead's not.
Okay. Pencil lead has graphite in it, but what else it has in it is kaolinite, which is a clay. It's a white clay material. That's what gives it the hardness. A softer lead pencil, you can smear it. You know, that's more graphite, less kaolinite. What's that?
You can hook a pencil on both sides of the battery and it catches fire.
Yeah, exactly. Because graphite is a good, it conducts electricity really quickly, and that heats up and explodes, and it burns real nicely too. So, graphite carbon is two-dimensional crystal structure. Diamond carbon is three-dimensional crystal structure. The crystals are totally different, so they have the bonding is totally different, so they have almost diametrically opposed qualities. Diamond is the most abrasive substance you have. If you have a diamond saw, you can cut through anything. Okay, diamond encrusted on the blades of a saw, cut through metal, cut through concrete, cut through anything. Graphite's a lubricant. You can't get much different from those two, and they're made out of exactly the same atoms, carbon. Now, you also have things that are in between conductors and insulators called semiconductors. They conduct or insulate depending on the circumstances, and applications for those are your computer chips, solar cells, things like that depend on semiconductors. And that's why one of the early ones was made out of silicon and silicon dioxide. Okay, some conditions that will transmit electricity easily, sometimes it won't, depending on the situation. And that's why the early manufacturers of computer chips, where were they located? Silicon Valley. No silicon in the valley. That's what it's called because we had all this silicon dioxide making the computer chips. Okay, that's why it got its name. Okay, so let's look at electric charge. The smallest piece of charge you can possibly have is a single electron charge. You can't break it down any smaller than that. But that's so incredibly tiny that that's microscopic, submicroscopic. To get something you can measure on a regular scale, you use the charge of a coulomb. Okay? And a coulomb is equivalent to the charge of 6.24 times 10 to the 18. That would be 6,240, 000, 000, 6 groups of threes. 6.24 with 16 zeros following it. That's how many electrons. I mean, it's an incredibly large number of electrons makes one. That's the metric unit of charge. Now, what do we use in the U.S. customary system? Coulombs, because you see, the metric system was established before they ever knew about coulombs of charge. Charles Coulomb, a French scientist who studied these things, and they named it after him. That's, by the way, why it's a capital C, by the way. Coulomb, capital C, is named after him. He came along after the metric system was put into place, so they defined it and said, well, everybody used it. The British, the French, everybody used it. So therefore, in fact, everything in electricity, there's only one set. The metric, SI, everybody uses those same things. Coulombs, amperes, volts, ohms, everything. Okay. So, the electron charge, that amount of a coulomb. The fundamental charge, you can't get any smaller charge than that. Smallest seen in nature. The quantity of the charge is related to the number of electrons. That's just a strange bullet there. It doesn't really make a lot of sense by itself.
Who came up with that figure? Off the top of my head, who came up with that specific number? That seems awful.
You know, I don't know the answer to that, except that.
Well, they have to be awful smart, wouldn't they?
Okay. Well, what they did, they got something they could measure, and they decided this, that, and then everything else came off of that, and they backed into it, as my guess. Okay. I don't think they said, well, let's just choose that number to be 1 coulomb.
In my,
It came from somewhere else.
I had AC here,
Yeah,
and I think that was in there.
I bet it was. Yeah.
Alternating current.
Yes. Well, in direct current too, they use the same thing. They use coulombs, which is that many electrons. So here's the equation for a quantity of charge. Little q, now remember in the last chapter, capital Q, in chapter 4, capital Q is E, remember? Now little q is charge. Okay, sorry about that. Not enough letters in the alphabet to cover everything, I guess. So they use Q for charge here. That's the number of electrons times the single electron charge. If that number n is this number here, then you have 1 coulomb of charge. If it's anything less than that, you have a fraction of that. Anything more than that, you have more than a coulomb, 1.3 or something like that coulomb of charge. Okay? So that's the formula that relates fundamental charge, electron charge, to the useful measure, which is coulombs. Okay. So here's that conversion, you might say. 1 electron charge is the number of coulomb charges divided by this, or if you write the reciprocal of this, that would be 1.60 times 10 to the minus 19 coulombs per electron. If anyone has a calculator that has a reciprocal key on it, it's either 1 over x or x to the minus 1. If you'll take your calculator and plug this number into it, 6.24 EE or EXP 18. Put that in your calculator. 6.24 EE or EXP 18. That means times 10 to the 18. Okay? Then find that key that's either 1 over x or x to the minus 1. Press that key. You might have to press equal, I don't know, but you'll get this number right here. Won't you? You don't?
I don't know how to type.
What's that?
I don't know how to type. Please don't know why.
Yeah, that would do it. Okay. What was that? 6.24. 6.24. 6.24 EE. That make it EE, there it is. 18. Whoa! Okay, that, then we want to X. No, okay, it changes. Okay, that's not what you do. This is a stranger calculator. 6.24 EE 18. Okay. Then do 1 over x. That. I don't know how to do it on this. Oh, let's try this one. Open parentheses. 6.24 EE. Why did it not take it the first time? Okay. 18. Close parentheses. Close parentheses. Why don't I do it? There it is. And then do 1 over x. There it is. Exactly that. So you had to put it in parentheses. It was doing it just to the x. And that was doing string trace things. Did you get it? Telephones do strange things with it. They're not set up to be calculated. So that is your conversion going back and forth. This is reciprocal of that. And that's reciprocal of that. Okay. Now, let's get to forces. Oh, before we get to forces, let's do example 6.1. So let's go back here and do example 6.1. Combing your hair on a day with low humidity, remember that's required, results in a comb with a negative charge on the order of 1. Ooh, let's get my dark pen here. Okay. 1.00, this is just a regular figure here, 1.00 times 10 to the minus 8 coulombs. That's a very low amount of coulombs. That would be 10 microcoulombs. No, even less than that. 100 microcoulombs. Really, really small number. No, that's not right. 0.001 microcoulombs or something like that. Okay. How many electrons are transferred from your hair to a comb? Doesn't sound like many, does it? Okay. Well, what we do is multiply the or divide this by 6.24 times 10 to the 18. 6.24 times 10 to the 18. That's electrons per coulomb. Okay? Or we could have multiplied that 1.00 times 10 to the minus 8. No, that wouldn't have given it to us. Okay. I think that's how we need to do it. See what no, I said it backwards. You multiply that. That's what I knew something was off here. You multiply this by that. Because the units won't work out otherwise. Or divide by the other one. Okay? So 1 times 10 to the minus 8 coulombs times 6.24 times 10 to the 18 electrons per coulomb. I can't get the pen to write. There it goes. Okay, electrons per coulomb. Coulombs cancel out, and what do you get? Well, it's pretty easy to do. 6.24 times 10 to the, you just subtract the 8 from the 18, 10 to the 10 electrons. Okay. That's, and usually you don't put the minus 1 there, you just put a minus. Okay. That's how many electrons, which would be 62 billions, 62.4 billion electrons. A pretty small number, okay? Very small number, okay? Now, the crazy thing, they did it the hard way. They divided by the other number, and they got a decimal out of place. If you multiply by that number, you get exactly the same number, 6.24, but it's now times 10 to the 10. They got 6.25 times 10 to the 10. That's because they divided by a rounded off number. Okay.
What is that number? I'm 6.24 times
10 to the 18.
10 to
Yeah, it's this number right here. electrons per coulomb.
Okay.
Okay? Yeah. Okay. Now, you know what? I forgot.
Looking at, they got 6.25 and then you explain.
Yeah. Okay. They got in the book 6.25 because they divided by the other number. Okay. All right. Now we're ready for electric forces, electrostatic forces. Okay. The guy who they named the thing after, this is what he did. He came up with this law. It's a law that shows a relationship between giving forces between two charges. So let's say we have a charge up here. What y'all want it to be, positive or negative? You choose. Positive charge here. And we have another charge over here. You want it positive or negative? Negative. So these two charges are going to be attracted to each other. The attraction is by a certain force. In other words, to keep them from colliding, you have to hold them apart. How much force do you have to apply? That's what Coulomb's law gives you. The relationship between the forces of giving the force between two charges. Similar to Newton's law of gravitation, which is two masses here, and they're attracted to each other. And what you find out is in Coulomb's law, the K, which is called the electrostatic constant, or Coulomb's constant, is so much bigger than G, which was the universal gravitational, implying that gravity is actually weaker than electrostatic forces. But we kind of knew that, because remember that comb? You didn't put many electrons on there. You can pick up pieces of paper overcoming the gravitational attraction, which keeps them on the desk. The electrostatic attraction picks them up. So it's a little bit stronger. The difference is gravitational forces work over enormous distances, whereas electrostatic forces have to work over very short distances. Very short distances compared. So here is Coulomb's law. F, this is the force of electrons. Okay, I don't know why that did it, because I tapped the board, I don't know. The electrostatic force is equal to the electrostatic constant, and look at that constant. 9.00 times 10 to the 9th Newton meter squared per Coulomb squared. And if you compare that with the G, which is the gravitational constant, which we'll do later, that has 10 to the minus 11. So the magnitudes are different here. Of course, they're measuring different things too. But you multiply Q1 times Q2, whereas gravitation was M1 times M2, divided by D squared, that's the same. Distance between the charges squared. Okay? That is the force due to electrostatic charges. Okay? Now, if I had asked you to give me how many coulombs in that charge up here, and how many coulombs in this one, and then you give me the distance between them, we could tell exactly what force was between those charges. Okay? So there is Coulomb's law. Here is Newton's law of gravitation. Look how similar they are. They put the K in front there. You could have put it up with the Q's. Here they put the G up with the M's. You could have put it in front. It doesn't matter. But look at the difference in magnitude. This is 6.67 times 10 to the minus 11. Now they missed the units here. Okay? That should be meter squared per kilogram squared. Okay? It's 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Whereas the other one was 9.00 times 10 to the 9th. I mean, that's multiple orders of magnitude stronger. Newton meter squared per coulomb squared. Of course, kilograms, coulombs, you can't really compare those. But that's how similar they are. Okay? So looking at the relative sizes of that, here they do it. And this, again, is not a very fair comparison because we're talking about different units. But 9 times 10 to the 9th divided by G, which is 6.67 times 10 to the minus 11, that would be 1.4 times 10 to the 20th. But again, that's not a very fair thing because this is dealing with coulombs, this is dealing with kilograms. You can't compare apples and oranges, but it just gives you a relative idea and sure that's quite a bit of difference. Quite a bit of difference. Okay. Oh, sorry. Let me,
Wait, no, back to the other part.
the last part?
Yeah. that-
Okay. All right. How are we doing time-wise? I forgot to bring up my watch. 5:43. I only got 2 minutes left. We're not going to get as far as I wanted to get, but because we were talking in the hall. After tonight, we only have 5 more classes. Okay? That means because I have to be gone the Thursday after Thanksgiving, that's only 4 more possible lab days. And we have 3 labs in this chapter and 1 in the next one. That's a lab every time. So we could get by without it tonight, but I hate sort of having a lab on the very last day of class. So if we don't have it on that last day of class, we need every class day we have to do a lab. So let's plan to do the lab tonight. We will not have covered everything we need for it, but it's pretty straightforward. In fact, I'm real tempted to stop right here. Oh, you got this now? The next slide is force fields, which is, we've got 2 examples. No, 1 example. Let's start with those examples next time. That example next time, example 6.2. Okay? And then we'll get started on force fields. Okay? Now, let me have you turn over in your book. Our lab tonight is on basically electric circuits. Okay? And if you turn a few pages, and unfortunately it's too many pages, we never would have gotten all this covered tonight. So really it wasn't going to do a good job preparing us for it anyway. So I'll explain everything to you when we get to lab, and we'll do that. I don't know why this is flicking like this, but we're going to shut down anyway. So if you will, let me go on and give you the lab. Yuck. So I don't have to haul them down there. And even though we just took a break not long ago, you get another break now because it's going to take me, as I told you before, a while. I've got all the equipment down there, but I couldn't set up because they had biology labs, and they needed the space, and it's their space. So here's what we're going to do in lab today. It's called electric circuits. And I'll try to explain everything as we do it tonight. All right. Y'all, I think it should be all that. For the automotive people, I think you probably done something like that. All right, who else didn't get a lab? That's okay. All right, it's going to take me a while to get broken down and back together, so I'll be down there in a few minutes. Take a bit of a break, and I'll get there. All right. Sorry, it's a little bit slow to get started here, but we're ready now. We have 16 people here, so we're going to have 5 per team, but one team's going to have 6. Okay? This one's got 4 right now. That one has 5. So that team needs 2 or 3 people. This team needs 2 or 3 people. No, 1 or 2 people. Okay? So move to either this table or that table. Get either 5 or 6. Okay? Hey, yeah, Move one someplace. Okay. Okay. You don't move there, you move there. Okay.
We related somehow. The soda is my favorite.
Okay. So you'll move to that table there. Okay. All right, folks. A little bit of ground rules here. We didn't get to talk about circuits today. I wish we had, so I'm going to try to hit as much as we do today. On an electric circuit, when you hear the word circuit, what comes to mind? Anything?
Electricity.
Okay, electricity for sure, but just any kind of circuit. Okay, circulation. Okay, very good idea. You need a complete loop to have a circuit. You can't have it dangling somewhere. So what we're going to be doing is electric circuits that complete a loop of some nature. Okay? Now, the procedure number 1, it says 1 flashlight battery, 1 bulb, and 1 piece of hookup wire. We're not going to do that. Here's what I want you to do. Okay? First, there's a figure 20.2 here. Oh, wait, I'm sorry. I meant to do this. Here is the symbology we'll be using. Okay? A battery is represented by a series of long and short lines, parallel lines. Are you listening? Y'all probably know this, but it's parallel. One line's long, one short, one long, one short. Now, basically what the pairs are, they're representing cells in a battery. Okay? For instance, a car battery typically has 6 cells, 2 volts each. That makes a 12-volt battery. Okay? Most of your batteries that go to the flashlight are about 1.5. So that's just one pair of electrodes of things that's making a cell, a single cell. Okay? You can have bigger ones. We had tractors that had 24-volt batteries. I've heard of heavy equipment that has 36-volt batteries. Big old things, lots of cells. This one represented here would be a 12-volt battery, okay, approximately. 3 cells, we'll say it that way. We're not going to use AC circuit, but with AC circuitry we use the ground symbol. Okay, we're not going to use that today. The bulb is going to be, and by the way, any resistance is going to be a jagged line like you see there, a resistor. If you put a circle around it, that means it's a resistor that happens to be a light bulb. That's what we're using today, the bulb. You don't have to put the circle in unless you want to. Okay? We're not using variable resistors, so that would be the symbol for that. We're not using switches today. Even though some of the diagrams show switches, we're not going to use them. So don't worry about that. When you see 2 wires that cross each other that don't have a dot in them, that means they're just crossing. They're not connected. This made a special thing of showing one jumping over the other. If you soon see a dot, that means they are connected there. We may have 1 or 2 that have connections. Yeah. No? Yeah, we do have 2 that have those connectors, 3 maybe. All right, so turn to the next page. The first thing here shows figure 20.2. Oh, I'm sorry. They got this sort of backwards. Okay? The 20.2 is procedure number 2. Note the construction of the flashlight bulb. That's what you see, 20.2. Okay? There's 2 things missing in it, though. It's an incomplete diagram of a bulb. Complete the diagram by drawing wires that connect the filament to the contact points in such a way that you get a complete circuit if you had it hooked up. Now here is actually something like a flashlight bulb. This is old and corroded. But you see there's a point here. That's the tip at the end. Okay? That has to make contact with the battery. Okay? So that tip at the very bottom, that would be this point. Then you have the outside casing. That makes the other side. Are y'all listening? Okay? Notice in between those you have some black plastic. What is black plastic or any color plastic? Insulator. Does not conduct electricity. So you have the tip down here separated from the casing. That's important because otherwise you would have a short in here. Now inside the bulb, and you can't really see it very easily, but there's a filament and two poles coming off the filament. One pole is connected to the tip and one to the casing. That makes your complete circuit. Okay, let's not mess with that stuff, please. Okay, thanks. All right, so what's missing in this flashlight bulb? The wires to connect. One connects to what? The tip, and the other connects to the casing. Okay? Because you see the casing is a conductor. So you draw two lines in that figure 20.2. One of those that's just hanging down there, not connected to anything, draw to the tip. The other, draw to the casing. Does that make sense? Do you have any doubt? I would use pencil as I were you, so you don't have to zig around with ink. Okay? What do you think it's going to be? One of these goes to, say, the casing, and the other one goes to the tip down here. Okay? Y'all got the idea? Okay, yeah, one to the casing, one to the tip. Excellent. Y'all got it? One to the casing, one to the tip, all the way to the tip. Okay. Notice the black there is their insulator that separates those two. All right, that was number 2 on the procedure. Everybody's got it?
Yes, sir.
Okay. Now let's go to number 1 on the procedure. And we're not doing a flashlight bulb, flashlight battery, flashlight bulb, and a piece of hookup wire. What we're going to do, if you look at the figure 20.3, it shows those 8 circuits at the bottom. You see them? Look at circuit number 1. Draw that circuit, but you don't even have to put the switch in it. Draw the battery, the bulb, and the rest of the lines are just your wiring. Okay? Now notice how the battery is. One big long wire and one little short line. Okay? Then you go to the bulb, and then you go back to the short line of the battery. Right? Draw it just like this. You can leave off the switch. That's what you draw in here. Okay? Now, what I didn't tell you before, but it's on the page, so turn back to the front page. Notice the battery is always, the plus side is the long side, and the minus side is the short side. Okay? Now, this is the part we didn't do in class. Okay? Now, but remember, this is important. Not super important, but it's just important to keep in mind. We have what we call conventional current. And the conventional current always goes, as everything does in physics, from high potential to low potential. Okay, it says positive is high and negative is low. In fact, some of you, I think, brought your books in, didn't you? Didn't I see a book somewhere? Okay. If any of you have your books, and if you don't, you can probably find someone who does. Okay? The figure 612 at the top of page 149 is going to illustrate exactly what we're talking about here. Figure 612 at the top of 149. Okay? Any of you, any team doesn't have a book? Does this thing back here have a book? Yeah, you have a book. Figure 612 on page, what did I say, 149? Is anyone listening? I was.
149 is like questions.
Second?
Okay. Yeah, 149 is like questions.
Say back another time.
Page 125.
Back another time.
Oh, you want figure?
Yeah. Yeah, it's figure 612.
There's 6.
That's example.
Keep going. Keep going. Keep going. Keep going. Page 125. Figure 612. Right there. Yeah. Okay. Everybody see that in the book? Figure 612 on page 125. Is that right? 125, 612. Okay. That's what you need to draw this to look like. Okay? You got the plus side of the battery. The conventional current flows from plus to minus, whereas the actual electron current, which is the move of the charge, that has to go from minus to plus because electrons are negatively charged. So you draw your arrows, one arrow showing conventional current and the other showing electron current. Okay? You'll see the words written in bold on page 179 on your lab, the front page of the lab, conventional current, electron current. Show the arrows showing which way each is going. Where does conventional current go? From plus to minus, and electron current goes from negative to positive. Exactly. Okay? So there's the first two parts of the lab. All right. Now, I've done the very first part of number 3. I've wired the circuit for you, each team, okay, with the power supplies on the bottom. That's the voltage source. And the numbers you'll read on that is volts, okay, when I turn it on, okay? And what you'll do when you turn it on, okay, the knob right here is going to adjust the voltage. Adjust it very slowly until you see the light come on. Okay? Now, when you have what you consider standard brightness, record the voltage. Okay? Don't turn the bulb on very bright. Just whoa. Wait a minute.
I'm trying to get a shape. My light is so turn it big.
It's 4.1 right
Record what the voltage is for a standard brightness. Okay, you're just doing right now.
Show the physics of fire.
4.1 volts. You just set the code somewhere.
Okay.
I just wrote it.
Now, whatever you want to be standard. Maybe a little brighter or less. You're happy with that. That's right. Record the voltage. Okay? Now, the question was, where do you record the voltage? Okay? Listen up. Number 1 says on results on page 181, using the brightness of a bulb in the simple circuit, number 1, that's the one we've got on now, as the standard for normal, okay, what you're going to do. So what I want you to do is you can write your voltage there by number 1. You can write your voltage on 183 under number 1. Simple circuit, observations, that's going to be your standard brightness. And you can put down the voltage there if you want to. Okay, once you've got that, turn it off so we don't run down the bulb. You can just hit that on-off button. Yeah, easy way to do it. Okay, do not get these bulbs super bright. You'll blow them, and then I don't have any backups. Okay. So everybody got what standard brightness? You know what it looks like, right? All right. So what you do next is connect number 2. This is 2 bulbs, and what I'm going to tell you this is, these are called in series. I'm going to move this over one so you have a little more room. Okay? Right. Okay. Now, that's too much. We are going to later. This is in series. Okay, now here's what you look for. Follow this line. This shows where, and you can see the soldering underneath there. It goes from this tip to that tip. These do not have connection. So this will be on the same bar, so that's the line, and then this needs to be there. Okay, that's in series.
So that's just kind of like.
All right, everybody got it in series? Got your other bulb. Here's the other bulb. Okay. And watch.
So they don't say that
So you follow this line.
you say you
The soldering under there goes right there.
you say you
We didn't use this.
I know it's still kind of the same.
Yeah.
Yeah. So it's given the break.
So stay behind the teacher that's speeding out here. Yeah, take a picture of the
There we go. Okay.
Still got that to take.
Okay, wait, no.
I still have to AC. That's what last
Okay.
class I have to take.
Everybody set up?
I have everything
Number
done
2.
except for AC.
Okay.
Like 2 electives. So next
All right, now from now on, we're going to the table and table alone. We'll come back and answer the questions later. So go to this table. Okay, so you got 2 things in mind. The figure here showing the circuits, and then the table over here that you put your information. Here are the 2 pieces of information, 2 pieces of information that you write down on every line, the observations. You got 2 bulbs in series. Oh, here's the other thing I forgot to tell you. Sorry. But back here, notice you had 1 cell in number 1, right? Look at number 2. 1 cell again. So that means you keep the same voltage you had before. Okay? Because that represents the voltage. Okay? So what you do with these in parallel, now here's the 2 questions you answer. The first, is the bulb, or bulbs in this case, brighter than normal, the standard, equal to the standard, or dimmer than the standard? One of those 3. Brighter, dimmer, or equal. Equal to the standard. The second one, after you've got that determined, then pull out one bulb and see what happens to the other bulb. Does it stay on or go out? Okay? Now don't pull it out of the thing, just pull it off the board. Pull the green thing out. The green thing off the board. Yeah. But wait, did you do the first part?
Yes, it was, they were dimmer.
Dimmer. Okay, this team had dimmer. What did y'all have? What did y'all have? Dimmer for sure. Okay. What did y'all have?
It was real dim, but now the circuit. The circuit's not.
So that would be dimmer or brighter or equal? Dimmer. Okay. Then we'll pull out one of those. No, not the bulb. What happens to the other bulb? Nothing happens. The bulb went out. Right? Those are the 2 observations you make for every circuit. Okay? And that's what you write in the table at the back. That's table 20.1 on page 183. Circuit 1, put down the voltage, say that's your standard. Circuit 2, brighter or dimmer, and what happens when you pull out one bulb?
Take out one against the circuit.
Okay. Now, circuit number 3, what do you notice about it? Which does it look more like? It looks like the first one. What's the only difference between it and 1? Yes, you have twice the battery, okay, the voltage. Don't do twice the voltage. Okay, so set it back up like you did the first one. Okay? Now this time, rather than doubling the voltage, just increase the voltage a little bit. That will enable you to answer the question. Just increase it a little bit. What happens? When you increase it just a little bit. It brighter. That's the only answer you have. There's no bulb to remove the second. So increasing the voltage, and certainly if you double the voltage, it would be much brighter. I don't want you to run out the bulb. So once you've determined that, turn it back off. Okay. Okay? So everybody got it?
Yeah, no, good.
Did you find that to be the case?
Not good.
Increase the voltage. Second?
This is too bad.
No, okay, we double the voltage. See, we are using battery. Okay, yeah, but I said don't do that because you might blow out the bulb. I said increase the voltage, you see what it does. If you're doing it.
I said we skip fall.
You're doing it.
Summer to winter.
We only have one bulb.
It does snow in spring.
Right.
I was like, you're gonna crank the car, it's snowing. I'm like, wait. And then you know what, true, and then people in the South be so extra for real snow.
You didn't answer the question of what happens when you take out one of the
I
bulbs.
want real snow.
Oh, no, I know.
I'm looking at that's fine off. Okay, good.
She had
I want to live where it's not like, I want to snowboard.
Yeah,
I also like my summertime.
Bulb, there's only one bulb, right?
But I want to live
Okay.
in,
You did it with two, you do it with one. Don't double the bulb, increase the bulb.
and then I'm gonna go deep for gold.
Like that.
And after that, so I'm go deep for gold in Africa or go.
Okay, has everybody got number 3 done? And again, look at the picture, everybody. Look at the picture to make sure you're doing the circuit that's in the picture, not leaving what's on the thing before. Don't leave the bulbs on too long. But once you've seen the result, don't leave the bulb on. I don't want it to blow out. Once you've seen, yeah, good, thank you. Okay. Okay, have you set up for number 4 yet?
yes.
Okay, I see one team has, 2 teams have, 13 set up for this one. No. Okay. Now, on this circuit, number 4, what's different from it from number 2? Yes, twice the voltage. This one you can crank up the voltage to twice what you had for 2. This one is okay to do that. Twice what you had for number 2. Did everybody hear that? Okay. What do you notice? 2 things you're supposed to notice. It is brighter than the standard. Go back and do standard. At the original voltage. Say again? No, okay. The voltage is twice, but you have 2 volts in there. How does that compare to standard? Like same as standard. Okay? Now what happens if you take one of the bulbs out? Okay? And the other light goes out. Is that right? Did you do it? Yeah. Right? Okay. That's right.
It don't like those.
It won't go up to 8.
It will not.
It's like my moon gets.
Okay. One of these is real picky.
Oh, well.
What is that? Yeah.
What is that equal to?
Yeah, that is equal to standard. Okay? Okay, then turn it off. Don't run down my bulb. Oh, did you find out what happened if you remove one of the bulbs? Okay? The other one goes out. Right? Okay. Has everybody, excuse me, remember you got 2 questions to answer on the table. Excuse me, is anyone listening?
Yes.
Okay. Are you listening? 2 questions to answer on the table. Brighter, dimmer, or equal. And number 2, what happens if a bulb goes out? Okay? Now, if you got that done for circuit 4, then do circuit 5. Ooh, this is going to take some wiring on this. That's why I got those little wires out. So if anyone doesn't know how to set this up, let me know and I'll try to help.
Yeah, I'll
Where's it going? Parallel.
We're going to do it parallel, but you
In the same.
okay. You can't do it. Okay, you're going to have to use the wire.
Yes. For fake phone.
Yeah.
Girl, I just
Okay. Anyone need any help with that? Not this wire, the little wire. The one over here.
Oh, the little one.
So the circuit and the current is two different things. The circuit and the current is two different things. No, I'm just asking.
Yeah.
High five. Okay. And so today the student revenue was closed because they like the Birmingham campus move, which I don't know why because they ghetto as fuck. But I like, yeah, girl, I hate that. So then, we went to the lecture, right? You know, one of them, I got my speaker.
Y'all know what to do? High side to high side.
They had two
You have
of
to do
them.
one side to one side.
They said them deep.
What you're doing there is
Number one is wire.
Okay. You have to connect.
So if it's like saying the first thing they did, and then this big black girl was like trying to bump my friend, and it's special. Cause her parents like this, like her wig was split. Is your pig that there? You need an extra hard though. But she like trying to bump my friend, and my friend had words. Cause she had her friend, so they would have jumped her. I should have put her out of my here.
You want us to drive it back to the 4.1?
What's that?
Do you want us to drive it back
to the standard?
Yeah, oh yeah, for sure. Okay. Yeah. Okay. Okay, 2 questions you answer. If you got it set up, go back to your original voltage. Because you notice number 5 is a single cell. Hey, original voltage. What was it? Okay, whatever you had, be sure you go back to that. Okay? Now, 2 questions you answer, what are they? Okay, brighter, dimmer, are they equal? And what do you have time?
Yeah, also this gas was tested by this.
Okay? And what's the second question?
I thought he heard me.
What happens when you remove one bulb? Remove one bulb.
He always died.
What?
Did you remove one bulb?
Remove one bulb.
Oh,
Remove the whole thing. Hold the whole thing out. No. Okay, leave it on. You gotta see what happens. Put it into the original bulb. You don't know what happens. What happens? Watch it. Whoa, no, the parallel, you still got a circuit there. Exactly. What happens when you remove one? Stay on. Okay, turn it off. Let's turn it off. Make your feet right. All right. Now, what's the only difference in 5 and 6? Okay, except this time we don't. We do it just like we did before. Increase the power just a little and see what happens. Just a little. What happens when you increase the power just a little? It gets brighter. What happens if you remove a bulb? Stays on. Very good. Make sure you understand that. Increase just a little. Don't double the voltage, but increase it just a little bit. Increase it. You got the wacko one.
It does weird things.
I know.
Just here.
So when you get it to go up a little bit, what happens? Okay? Brighter? What happens when you move the bulb? Oh, good deal. Turn it on. Okay. Once you have the data, turn it off, please. Okay. Now we're not going to wire number 7. I want you to think through number 7. What you notice is number 7. Rather than one of the lights they just connect a wire across there. What do you reckon is going to happen? What's that?
Bypass the bulb.
Yes, exactly. You short circuit the circuit. In other words, all the current. Think of current, okay? Think of current as being like a student. Always follows the path of least resistance, right? Just like students, right? Okay. Okay. So if you wire it, that's why I don't want you to do it, because if you did that, your wire would get hot, probably bubble up the insulation on it, and it wouldn't be any good after that. Okay. So you call that a short circuit. Now, how do you tell a short circuit from an open circuit? Just looking at it.
An open circuit has no current.
Okay, but the thing is, looking at it, the bulb looks exactly the same. A short circuit is far more dangerous, so you could then have a fire. So just looking at the bulbs, neither of them come up. Okay, but with a short circuit, it's because something has found another pathway. With an open circuit, there is no pathway. Okay, that wasn't part of the problem, but whatever.
So we have to just like short circuit.
Say again?
We have to just like short circuit.
Okay, my hearing is so bad, someone doesn't tell me.
So we have to just like short circuit.
That would be fine, but read what it says for number 7 on your diagram. Circuits have one bulb in parallel with a wire. Don't do it, but just think about it. Show with arrows how the current takes the path of least resistance. So draw your circuit like you see, or you can use the one back here and draw where you think the current's going to go there. Does it split and some current go through the wire and some through the bulb? No, because the bulb has more resistance, it all goes through the wire. Nothing goes through the current. Okay? Through the bulb, sorry. Okay? No, this is number 7. That's what we're doing now. Do you understand what we're talking about? Right. Yeah. And it says draw. Show with arrows how the current takes the path of least resistance. So either draw the circuit here, or you can draw it on here. Where does the current go?
I did that before.
Forget about the switch. The current here. Where does it go? Does it split? Some goes through the bulb, some goes through the wire. All through the wire, nothing through the bulb. That's what the bulb looks like. Remember, the current is like the receiver. As far as the path of least resistance, right? That's the kind of okay. Now, if you look at number 8 carefully, oh, there it is. Number 8. Number 8 is really just like number 6. So you don't have to do a thing. It just put an extra switch in there. We're not doing any switches. So number 8 is just like number 6. So you don't have to do another thing for it. Answer the same way you did 6. Okay? Now, if you're certain you've got the table filled in correctly, and what do you put on the table? Brightness or dimness are the same, right? Or, and, whether the bulb goes out or not when you remove the other bulb. Okay? Now, and number 8 will be just like 6. If you did 6 right, you're okay. Now, okay. Yes. Draw like this, or you can draw where the current flows. That's it. Absolutely right. Okay. Now, if everybody's gotten all the tables done correctly, hopefully correctly, okay, then what you do is go back to page 181 and 182. 181 is just talking about that first thing, but then it says, using the brightness of the bulb in circuit 1 as standard for normal, describe which circuits had bulbs that were of normal brightness. Okay? Go back to your table and see which circuits had normal brightness. That's all you put, the circuit numbers that had normal brightness. Okay, number 2, it says which circuits had bulbs that were dimmer than normal. Okay, now that one you just do the circuits that were dimmer than normal, but then there's a second part. Explain. Why were they dimmer than normal? If you don't answer the explain, you're going to lose some points. Okay? Number 1 doesn't have an explain, you just put the number of circuits that were standard brightness. Number 2, which circuits were dimmer than normal, explain. Okay? Number 3, which circuits had bulbs that were brighter than normal. Go back to your table, figure out which ones were brighter, write those circuits down, but then you explain. Right? And some of the explanations will be a little more complicated than others. Okay? Number 4 on the next side, in which circuits is removing one bulb cause the other to go out. Look at your table, and those that let it go out, put those circuits down, but then explain why. Then in question 5, which is removing one bulb not affect the other, in other words, the light stayed on, write down which circuits those were, and then explain why. And then number 6 and number 7. Number 6 has a specific answer, and number 7 just needs your answer. Okay? Now you can do this in here, or you can go back to the classroom and do it. I don't care. Huh? Okay, that's fine. And that way, if you do need to do something else on the setup, you can. Okay. Are there any questions? Okay. I'm going to, if you think there's going to be no questions, I'll shut down and have this upload. But if you think there may be questions, I'll just turn it off for now and turn it back on when there are questions. What you think? Questions or no questions? None? Okay. I'm going to start uploading then.